I think that the best way to really understand how an SPH algorithm works is to understand how it computes the density. So let's ask ourselves this simple question. So how do we compute the density from a collection of mass particles, of particles with a given mass? And here I'm showing you three different ways, three possible ways. And I'm going to discuss about the three of them and showing you the last one, that is the SPH one, why this is, how this works. So the first one is to simply constructing a mesh. So we divide our space in cells, and basically we compute the density in each cell by summing the mass of the particle inside each cell, dividing by the volume of the cell. So these methods are called, for example, particle in cell, cloud in cell. This is an Eulerian, let's say, way to compute the density, because you are building a mesh, you're building a grid. And this is very easy to implement, but this doesn't work very well when you have like dense region or sparse region. So if you have like a big gradient of density in your domain, the method doesn't work well. And because it can underestimate or overestimate sparse or clustered regions. Then a second method, which is like a step forward to, say, to a Lagrangian method, is to locally sampling the density by basically building a sphere centered either on particles or in a given point in our domain. So we build this sphere that can, and the radius of this sphere can be adapted, for example, to the local density. And yeah, the density then is just the sum of the particles inside of the sphere over the volume of the sphere. So this is better compared to before because it can be adapted to solve better sparse or dense region in the domain. However, this method turns out to be very noisy, because if a particle is right inside or outside of the sphere, then the density estimate can change drastically. And so then the last method, which is the SPH method, so the method that SPH uses, is similar to the one I showed you just before, but with let's say an improvement. The idea is that with SPH, we sample the density in a given location of the domain. Usually this location corresponds to the location of a particle. And the density estimator can be written in this way. So it's a weighted summation over nearby particles. So the idea is that at a given location, we sum the mass of the particles around this location, and we weight the sum with this weighting function, which is called the smoothing kernel, which is weighting more particles close to the location where we are computing the density and less the particles that are farther away. And the typical fall-off scale of this smoothing kernel is called H, and is the smoothing length. And then now the point is to basically choose a good smoothing kernel, so a good functional form for the smoothing kernel to have the best density estimate we can. And of course, the smoothing kernel must have some properties, so it must decrease with the distance compared to the position where we are computing density. So you see that it's a function of the distance between a particle E and a given particle J, and should be symmetric compared to the distance, of course. And the inner region must be flat, let's say, because we don't want that a small displacement of a very close-in particle changes the density estimate. And so, of course, a natural choice for a smoothing kernel is a Gaussian, because the Gaussian has all these properties. But there is a problem with the Gaussian, because in this case, it requires to compute the interaction between every pair of particles, because the Gaussian, let's say, doesn't have an edge, call it like this. And so this makes the density estimation very, very complicated and very computationally expensive, since the complexity of, in this case, scales as the number of particles to the power of 2. Okay. And so a solution we use in SPH particles is to basically choose a smoothing kernel that are truncated Gaussians, let's say. These are called the B-spline functions, and basically is a truncated Gaussian, and you can there are different orders of truncation. Usually in SPH code, we use either the quartic or the quintic smoothing kernel, and the idea is that it's basically a Gaussian, but at some point it goes to 0, so it's normalized, of course. And so the idea is that if we use one of these functions, the number of particles we need to compute, the pair of particles we need to compute the interaction is not the entire number of particles in the simulation, but is just basically the particles that are in the surrounding area, just the neighbors of the location where we compute the density. And as I told you before, this smoothing kernel also has this fall-off scale, which is called smoothing length. And the choice of the smoothing length in this case also is very important. So in general, in the very first SPH code, so the smoothing length, so this h was chosen to be constant throughout all the simulation, all the inside the domain. But this is, of course, it works better compared to the density estimate I showed you before, but still we want the smoothing length to adapt according to the local density, according to the local resolution. And so basically what happens in a modern SPH code, for example, in Phantom, is that we use the first equation to compute the density, where HA is the smoothing length of the particle A, because we are computing the density at the location of the particle A, and the smoothing length itself depends on the density of the particle A. So these are equations with, and we need to find the value of rho and the value of H. And so the idea is that these equations are mutually, of course, are mutually dependent, and they can be simultaneously solved with, for example, Rapson method or with bisection method. So there are couple of interactions, and then we can solve simultaneously H and rho. So H here, you see, it's proportional basically to the it's 1 over the number density of the particles, and D here is just the dimension of the problem. So like in 3D is just 3D. Eta is just a numerical coefficient. We usually set it to be equal to 1.2 because basically this eta is determining how many neighbors you have. So on how many neighbors you compute the density, and with an eta of 1.2, more or less the number of neighboring particles is of the order of 50 to 60. And this can be changed, this is found to be like a good compromise between precision and computational cost. Okay, so now I will show you a couple of equations. I don't want really you to understand completely what they say, but it's just to show you what are the hypotheses we make to obtain the evolution equations for the fluid quantities in SPH. And a very important thing to point out is that when we want to write a fully conservative SPH algorithm, with fully conservative, I mean that the angular momentum and the energy are conserved, like exactly conserved in the simulation. The only degree of freedom is basically how we compute the density. So that's why I spent some time in showing you exactly how we compute the density, because this smoothed summation of neighboring particles will basically be just the only degree of freedom we have when we want to write a conservative algorithm. And so the idea is that we want to go from this density estimate to the fluid equations. And so a possible way is just to write the Lagrangian of the discrete Lagrangian of the fluid. So basically, we are summing the contribution of each particle inside our domain. And so basically, this is summing mv, so the mass of the particles, the kinetic energy, minus here, U is just a thermal energy contribution. So UB is the thermal energy and depends on the density of the particle B, and SB is just the entropy particle. And this is basically the discrete version of the continuum Lagrangian. And to obtain the equation of motions, as you may know, we just use the least action principle. So we compute a small displacement of the action, where the action is the temporal derivative of the Lagrangian. And basically you can, I mean, I don't want to go through this, but just to show you that we are not like inventing anything. So these are just the calculation one needs to perform if wants to obtain the evolution equation. So after these calculation, which are just like simple derivatives, one can get the, of course, the equation of motions in like a very standard way. And here, the only hypothesis we are making is that the Lagrangian is differentiable, so it has no discontinuities. This is, let's say, most of the cases, this is okay, but of course, as you know, when you have, for example, shocks, shocks are discontinuities in fluid quantities as the density, temperature, velocity. And so dealing with shocks is a bit delicate with SPH, and I will show you later what one needs to do when dealing with shocks. So, okay, basically here we have this equation. These are the equation of motions. Yeah, and as I told you, so these are the hypotheses. So Lagrangian is differentiable, and also here we are not considering the fact that the time integral is discrete. So of course we are not like integrating. Of course, also the time is like a discrete variable, because we are, of course, we can't follow the time continuously. We just we need to divide the evolution in time steps, of course. And so the only, let's say, errors compared to like just the exact conservation of energy come from the integration errors of the algorithm. So this is just the other hypothesis. And okay, so basically, if we go back and we really want to write these other Lagrangian equations, so we take our Lagrangian, we can compute the derivative of the Lagrangian compared to the velocity, the derivative of the Lagrangian compared to the position. And here we just need to, we assume that the entropy is constant, so we don't have dissipation, okay? And also we need to like use the thermodynamics, the first principle here, basically to relate to basically compute the derivative of the internal energy with respect to the density. So we just use the first principle of thermodynamics, assuming that the entropy is constant here. And so basically the derivative of the internal energy with respect to the density is just the pressure over the density to the power of 2. And so within this, then one can compute is the spatial and temporal derivative of the density estimator. So the idea here is that you see here, in order to obtain the fluid equation, we need to compute these quantities. So this derivative here, and also we will need to compute temporal derivatives of the density. And now the way in which we compute the density is important, because basically the spatial and temporal derivatives of the density are just the spatial and temporal derivative of our density estimator. So basically everything relates to derivatives of the smoothing kernel, okay? So this is, for example, on the first line, you see what is the derivative of the density with respect to the position, which basically just translates into a derivative of the smoothing kernel. And here basically these delta are just taking into account when the particle A and the particle B are the same one. Yes?
I wanted to ask about the constant entropy assumption.
Yeah.
So, like, in any physical process, entropy should increase, right? So how important is that constant?
It's constant globally, let's say. So it doesn't change globally. So the one you have in the simulation remains the same. Yeah. Then locally can change, of course, but globally not.
So the entropy can be different at different spatial locations.
Yeah.
Right? If that is the case, then for the del L over del R equation, would you also need a derivative of the entropy with respect to the R coordinate?
Yes. Okay. Yeah. So here I'm showing you. Okay. So the constant entropy hypothesis is, as I told you before, like globally. Here in this calculation, I'm showing you just the simple case of also constant entropy over space. It is possible to generalize it to like entropy, which is varying with space. Here I'm just to show you like to get an idea of the equations. I'm just showing you the simple case where it's constant also spatially. And yeah, so basically, as I told you before, once we define the density estimator, then we can compute these quantities. And if you're interested in the actual calculations, I can give probably in the Google Drive folder you find also a paper for reference. But yeah, so the idea is that we can compute the spatial and temporal derivative of the density estimator just by defining the smoothing kernel. And so if we put everything together, these are the final equations that an SPH in an SPH under an SPH perspective. So the idea is that the first one is how we compute the density. The second one is we can, let's say, combine all the different pieces I showed you before to obtain how the velocity changes as a function of time. And this is basically the SPH version of the Euler equation. And then we can do the same also for the internal energy, and this is basically the evolution of the thermal energy in an SPH approach. So here you see that the quantities we have are the pressure, for example, at the location of the A particle, mass of the particles, derivative of the smoothing kernel compared to different quantities, and this omega B is just a numerical factor that is basically taking into account all just numerical constants that comes from the derivation of these equations. And then, of course, these are like the simplest equation. What we can do is to add, for example, external forces in the Euler equation. So whatever force you want to think about, like, I don't know, for example, a gravitational potential generated by a point mass, or the self-gravity of the fluid, so also the self-gravitating contribution of the fluid itself. Of course, these quantities needs to be like discretized in an SPH way, but is basically following the same idea I showed you before. And also, for example, for the evolution of the internal energy, we can add, for example, some heating terms due to whatever processes you want to think about, irradiation from stars, or cooling terms, for example, radiated cooling. Of course, all these terms need to be discretized in the correct way, following this SPH formalism. And yeah, I remind you that if you really want to see, for example, how you can discretize a gravitational potential or a radiative cooling term, I will send you the references to see what exactly you need to do. It's just math. There's nothing particularly interesting, I think, within it. Okay, so I think, yeah.
So you have 6 quantities to determine here: density, 3 velocities, pressure, and energy, but 5 equations. So I imagine you need some sort of a equation of states.
Yes, of course. You need to close the equation. You need an equation of state, of course. So you need to determine whether you need to decide whether your fluid is, for example, is locally isothermal, it's adiabatic, and the equation of state is the other degree of freedom. But this is just, I mean, you don't need to discretize anything in that case. It's just a relationship between basically pressure and density and possibly temperature. So the equation of state is, of course, something else to take into account. So do you have any questions so far about these equations? So basically, these are the equations that an SPH code evolves as a function of time, and to basically compute the different formations. Yes.
At this point, there's as I'm sure you're aware, there's a number of SPH codes and implementations out there, from everything up until now, which is the kind of the basics of the underlying hood of SPH. Are codes differing a lot up until here, or is it all going to be in these red additional physics?
No, let's say up until here, they are pretty much the same. So a degree of freedom, so like something you can change in different SPH code is, for example, the choice of the smoothing kernel, which is, I mean, it's just like a choice. There's nothing really physical within it. And but let me think if there's something like any other big things that can change. No, but I think like up to this point, like any SPH code needs to evolve this kind of equations. Yeah.
Actually, I don't know. We haven't really gotten into materials yet, or if there's multi-materials, but equal mass versus equal volume of particles.
Oh, okay. So here, in these exact equations, I'm making the hypothesis that the mass of all particles is the same, but this can be relaxed. So you can have like this different summation on different mass of particles, and you can have also different kind of particles that have different characteristics, different equation of state, coupling between them. But this is like all additional physics you add on top of this. But yeah, apart from that, these equations are valid for like astrophysical fluids, but also for liquids, also for solids. So if you simulate solids, is the same thing. For example, collisions of cars sometimes are simulated with the SPH. Yeah.
I have a question about discontinuities.
Oh, yeah.
Right, because once you smooth things with the kernel, those get harder to capture. So to say to capture a shock or something like that is the trick that when you solve for density and the smoothing length, you hope to get a very small smoothing length.
Now, the problem here is that these equations are not valid when you have a shock. So you need to add something else to capture the shocks, because as I showed you before, the biggest hypothesis we've made so far is that the Lagrangian and so the physical quantities are differentiable. So if you have a discontinuity, this is a problem. So up to now, a code like this cannot handle discontinuities, and we need to add something else. And okay, this is the slide I wanted to show. But before that, do you have any other questions on this? Yeah.
So about the resolution, what dictates the resolution of an SPH simulation? Is it the mass, or is it this?
It's the number of particles. Let's say it's the number of particles. Okay. 7. Okay. Yeah, it's the number of particles that dictates the resolution. And because the resolution element here is the actual particle, as in, for example, in a grid code is the size of the number of the cells. And of course, according to the different problems, you want to determine a resolution requirements. For example, I work a lot on disks. So disks in 3D has also a thickness, of course, and there let's say the resolution requirement is that you want to resolve enough the thickness of the disk. So you want that the ratio between, for example, the smoothing length of the particle and the thickness of the disk is smaller than, I don't know, 10%, something like this, so that you have 10 particles to resolve a scale height. But eventually this requirement really reduces to just a requirement in terms of number of particles. So the bigger is the number of particles, the better is the result. And just to give you an idea, we will see it later in the example, but just to give you an idea, like state-of-the-art SPH simulations, like the one, for example, we publish in papers, usually have never less than 1 million particles. And of course, 1 million particles is a lot, sometimes it's not enough, sometimes is enough. But of course, it really depends on the physics you put inside. Because of course, 1 million particle simulation can be really fast. For example, if you just simulate a very simple system. But if you start adding, I don't know, self-gravity, irradiation, and so on, then it may become really computationally expensive. Okay, other questions, curiosities? Okay, so let's go to the dissipation. So this is probably the biggest problem in SPH, and this is also the biggest thing people complain about SPH. So as I told you, SPH failed, the SPH, let's say, equation I showed you so far, fail in modeling discontinuities because we made the hypothesis that there are no discontinuities. So whenever we have shocks, there are the code will give you a wrong result. So basically, if there are shocks, what happens is that there is, for example, particle interpretation or numerical oscillations that are not physical, are just numerical artifacts because our equations are not valid in that limit. And so the idea is that one needs to add into this second equation another term that is, let's say, an evolution of the velocity dictated by a viscosity, while here, viscosity is like an artificial viscosity, is not an actual viscosity because we made the hypothesis that there is no dissipation. And so I don't like calling it artificial viscosity because it seems fake. So I think the right way to call it is shock capturing viscosity. So we basically add this viscous-like term that makes us able to capture and to model shocks. So the idea is that this will just want just to show you this term is can be written in this way, where pi AB is just a tensor that describes this viscous contribution. And it is that this term activates only when that condition is met. So when you have basically a convergence of fluids, okay? And the problem is that you may have physical scenarios where you have a convergence of a fluid, but without a shock. And so the idea is that in this case, you are activating this viscous-like term whenever when you don't need it. So a problem that people usually say about SPH is that it's too viscous. So because since we added this viscous-like term, the idea is that we are adding viscosity also when it's not needed. I think, you can find hundreds of papers about this, studying different numerical solutions for the problem. They are very technical. I don't understand most of them, so I don't think it's really worth going into the detail of this. But I wanted to talk about this numerical trick that is actually used in Phantom and in the modern SPH code. These are called switch. It's called switch. So basically, this switch tries to. It is that it activates the viscosity only when you actually have an actual compression with a shock. So, for example, if you have a shear, like I don't know, in a disk around a star, you don't activate this shock capturing viscosity. The way it works is really complicated. If you want, I can give you references, but it's mostly just a numerical. It's just a numerical trick to try to minimize the effects of the viscosity. But let's say something you need to take into account whenever you use this shock capturing viscosity is that the amount of viscosity you are adding depends on the resolution. So if the resolution is too low, then the amount of shock capturing viscosity will increase quite significantly. And so the idea is that if you want to, for example, simulate systems with a very low viscosity, like fluid with very low viscosity, you want this contribution to be as small as possible. And so you want really high resolution. And yeah, so this is another like resolution requirement that it's really important for the for viscous characterization of the system. So yeah.
So if the fluid has real viscosity, like if it inherently has dissipation, how do you model that? Can you just add a viscosity term to the Euler equation?
You need to add it like this. Yeah. Okay. You add it like this, and then basically the shape, the form of this tensor PAB will depend on the nature of viscosity you choose. So for example, if it's I always speak about this because this is what I do, but like for the planetary disk, if you have like an alpha-like viscosity, you can like prescribe it inside that. But for example, if you simulate like, I don't know, a glass of water that has a viscosity, you can write the characteristics of the viscosity inside that tensor. Yeah. Okay. So I hope this answered your questions about viscosity. And okay. Phantom. So Phantom is publicly available SPH code. It was developed by Daniel Price at Monash University in Melbourne in Australia. And here you have like useful links. So the documentation and the GitHub page. So the code is open source. So if after this workshop you fell in love with SPH and you start working with Phantom and you have new ideas, you can write new routines, just make a pull request, and if works, it can be added to the official code. And yeah, this code is a CPU-based code. Let's say, from different scaling tests, we found that it's very efficient up to 40 cores. Of course, it depends on the physics. The more complicated the physics, the higher is the efficiency, also for a higher number of cores. And it runs just on a single node. And this code is widely used in astrophysical community. And in particular, this is used a lot in accretion physics, so in accretion disks, but also in, for example, molecular cloud collapse, so for star formation, stellar evolution, and stellar winds. You can really simulate a lot of different phenomena with this code. And now I just would like to talk about a couple of characteristics of this code in particular, but in general, I think they can be applied to any different SPH codes. So in an SPH code, as I was mentioning before, you have different kind of SPH particles. So different kind, meaning that they can have different properties, different equation of states, different mass, and so on, and also different role inside the simulation. For example, a first kind of particle can be sinc particles. These are massive particles that are not, let's say, they don't have like a density or a temperature or a fluid quantity. They are just basically, they are sinc. So they're usually used to simulate stars, black holes in the simulation. So they are basically the center of gravity sometimes of the simulation. And they have an accretion radius, meaning that all the material that is falling within this radius is accreted by the particle. So the particle, this sinc particle, changes in mass. It can just accrete particles. I mean, you can also prescribe like ejection of particles, but in standard is just for sinc particle to accrete the material. And when a a particle is accreted by this sinc particle is giving the sinc particle the mass, but also the momentum. So the position of a sinc particle in a simulation can change. So it's not like a fixed potential as, for example, in some grid codes, where you have just a fixed potential that does not change as a function of time. And also in SPH, you can substitute sinc particle with potential. So for example, if you want to model, for example, GR effects, you can prescribe a GR potential. And yeah, so as I told you, usually we use this for stars, for planets, black holes, and so on. Where the idea is that we don't really want to understand what's going on at the surface of this particle. We just want, like, if a particle is too close to this one, it's just accreted and disappear from the simulation. Then we have the classic SPH particles. So basically, the particles that are described by the equations I showed you before. These may be, for example, gas particles. So there are particles with a pressure, so with an equation of state, and they evolve according to the equation I showed you before. And for example, yeah, these are usually like gas particles or in general fluid particles in a simulation. And then we have like, I call them dust-like particles. They can also be called like dark matter particles. So these are different kind of particles because these are pressureless particles, and they are also inviscid particles. So they don't have this shock capturing viscosity term, and they have a smoothing length. They may have different kernels according to like what they actually are. For example, dust particles in SPH tends to have a different kernel compared to gas particles. They evolve according to like a set of SPH equations, which may be the one before, but for example, without the pressure term, or with a different pressure term, with a different equation of state, whatever you want. And yeah, so usually these are dust particles in, for example, accretion disks, but also dark matter particles. If you want, for example, to simulate a galaxy, you can add these dark matter particles. And different kind of particles in a code can be coupled. So they may have like a force which depends on the two of them. For example, if the fluid is self-gravitating, if a gas disk is self-gravitating, then the dust particles can feel the self-gravity of the gas, so can feel this gravitational potential, so they can be coupled gravitationally, but also they can be coupled like with, for example, a drag force, so a force that depends on the difference of velocity between these different sets of particles. Yeah?
Do we have an equation of state for dark matter?
So I've never used dark matter particles in an SPH. I think it's just since they are pressureless, you don't have pressure, so you just can compute the density according to the position of particles. Yeah, I think it's like this. Yeah.
And in my experience, I can't remember whether it was conservation of mass that mattered or conservation of number of particles. So with the sinc particles, are you removing?
Yeah, the particles are removed. Yeah. But you are since when a particle, so the mass is conserved globally because the mass of the particle that is deleted from the simulation is then transferred to the sinc, and the same thing for the energy and for the angular momentum, because you basically the momentum of the particle is transferred to the sinc particle
Instead?
Not in, you can also in spin, yes, usually we just in like linear momentum. You can also do it with spin, yeah. I've never done it, but yeah. Yeah, for example, because usually for stars, it's not super important, like this rotation that gas particles can give to the star is negligible. But for example, if you simulate the black hole, then the spin of the black hole can be evolved as well during the simulation and can like be determined by also accretion of particles. So yeah. Mm-hmm.
But there's no numerical effects, or if there are, they've been solved for deleting particles, and how that the reduction of particles over time doesn't affect the integration.
No. So what happens is that, of course, what if you remove particles because they are accreted, the resolution is decreasing.
Increasing over time.
Yeah. So usually, when we run this kind of simulation, the number of accreted particles is not really comparable total amount. So, for example, for a standard accretion simulation, if you start with a million particle, like you can study whatever process happening there, but usually you don't lose more than, let's say, I think the maximum is 10% of the particles, but if you really evolve for a long time, there are then, of course, I mean, this kind of codes, you can add a lot of different features. So, for example, you can inject new particles. You can split particles at some point of the simulation to increase the resolution. So, for example, if you're accreting too many particles, you want to have high resolution, you can just split particles. There is also a new routine which is called adaptive particle refinement. So the idea, you can define zones in the simulation where if a particle enters in the zone, the particle splits into two particles or into 4, into 16, how many particles you want, to basically resolve better some region of the simulation and under-resolve other regions where you don't really care about what's going on. Of course, I mean, all these features, so like adding particles, splitting particles, brings an error, brings a noise, which of course over a long time can be significant. But of course, I mean, in SPH, I think that if you have a problem, if you increase the resolution, usually it helps. So increasing the resolution really helps reducing numerical noise.
When you want self-gravity, how do you compute the gravitational potential at each point? You use some n-body algorithm?
No, so to do so, you basically build a tree. So the idea is that you divide the particles in this tree, and you basically compute, you sum the mass of the particles in each little part of this tree, and you compute what is the contribution to different parts of the simulation. As you can imagine, since particle is global, since self-gravity is a global force, you need to compute this in principle within each pair of particles. What you eventually do is just to divide the simulation into chunks and do this, but still it's computationally expensive. So whenever you turn on self-gravity in an SPH simulation, the computational time increases. Okay. Other questions about these different kind of particles? Okay, if not, so finding neighbors. So as I told you at the beginning, we compute the density by summing the mass of neighboring particles and weighting the mass of the neighboring particles according to their distance from the location where we are computing the particle. And the idea is that for a particle in a given point of the simulation, we want to, the density there is just determined by the neighboring particles, not by the very far particles. But of course, you don't know what is the distance between two particles, you need to compute it. And so if you compute the distance between each pair of particles, you can imagine that this becomes computationally inexpensive, computationally very, very, it's a very long process. And so one of the key elements of an SPH algorithm is to have a good neighbor finding algorithm. And this is also very important, as I was telling you before, about for when you use the self-gravity. And in general, this is always the most expensive part of an SPH run. And the solution adopted by Phantom, for example, is to use KD3. So you may have used this KD3 also for your analysis and your work. So the idea is just you take your space and you sort it in, you divide it in boxes, and this procedure is pretty fast. And so when you want to compute the density in a given point, you will take into account just the nearby boxes and not all the particles. And this is very efficient way to find neighbors and to then compute density, but still remains one of the most difficult part of the speech algorithm. Okay, so what can we simulate? We can simulate a lot of different things. So of course, this code is adapted to like astrophysical scenarios. Like in general, you can use it for also other non-astrophysical problems. But for example, you can simulate hydrodynamical instabilities. You can simulate planet-disk interactions. You can simulate like any kind of geometry. So for example, this is like very distorted geometries. You can simulate inflow or outflows from stars, for example. You can simulate the collapse of molecular clouds to study the formation of stars. So you can really simulate a lot of different astrophysical scenarios. And in principle, I mean, you can also implement new ideas and new setups, because it is that you just need to implement the physics, but the evolution of the quantities is already written in the code. So it's just a matter of adapting your physics to the code. Okay, so now we can start using the code if you're okay. Do you have any question, any general question on SPH, grid codes, Lagrangian codes, whatever? Also, curiosity is really, I mean, whatever you have in your mind, please ask me.
How do you set initial conditions?
Okay, so you can decide. You can do whatever you want, really. So usually the standard way we set the initial conditions in with Phantom is to basically prescribe usually, I mean, depending on the problem. But for example, I don't know, for a star, we prescribe an initial density profile, and then we with the Monte Carlo algorithm, we just create a collection of particles which distribution matches this initial profile we want. And then there are actually some relaxation routines for most of the problems. For example, for a star, we will do it later. So this is, for example, you can this is a molecular cloud, but you can think about this as a star now. So you see, this is an initial condition. It's a bit noisy, of course, because particles are just randomly positioned there in order to like match a prescribed density, but they are just random. So the idea is that there are a couple of relaxation rounds where this system is just evolving, and the relaxation phase ends whenever, for example, in this case, the star's structural equation are solved with like a very small amount of error. But you can decide whatever you want. So you can, in principle, also write a Python code where you prescribe the position of 1 million particle in any way and give it to Phantom, and just use that.
We'll probably look at this later, but clump finding.
Yeah, there is. So this is, I think, related to also to the sync particles. So there may be like problems where you have collapse. For example, star formation. Also in accretion disk, you can have like collapse of a part of the simulation, and it's possible to create during the simulation sync particles. So, for example, when you make a molecular cloud collapse, at some point, if the density, for example, is higher than a given threshold, you can just put a sync particle there, and so simulation becomes less expensive. And there are conditions for a sync particle to be created. So the density must be higher than a given threshold, and also there are some checks regarding the energy. So you want that the gravitational energy is higher than twice the thermal or the thermal energy. Like it's a virial condition, and you can. In general, you can modify this if you have like your own conditions of clump creation. You can just implement them. Other questions? I mean, I don't know what you exactly work on, but I mean, for a lot of astrophysical scenarios, I think an SPH code may be useful. So yeah, from star formation to planet formation to galaxies. I don't know if you, I mean, usually your field, do people use SPH simulations or it's mostly grid simulations?
Both.
Both? Okay. What's your field?
I build simulations of galaxies.
Okay, yeah, so yeah. Okay, there are also, it's also possible to use SPH codes for cosmology, I know. And the Phantom actually is not, I mean, there are no existing setups for this kind of scenarios, but there is another very famous SPH code called Gadget, which is largely used in cosmology, especially. Okay, other curiosities?
So can you deal with fluid interfaces in SPH?
What do you mean exactly?
So suppose you have two different density fluids and suppose one type of fluid is colliding with another type of fluid.
Yeah,
like galactic outflows or
yeah,
outflows.
Yeah, you can. Yeah, you can. For example, I mean, this makes me think also about like Kelvin-Helmholtz instabilities. You can get Kelvin-Helmholtz instability in with SPH very precisely, actually. Yeah. So this is possible. Yeah, usually SPH simulations are global simulations. So, for example, if you simulate a galaxy, you simulate the whole galaxy. But sometimes you can also like do a local simulation with SPH. For example, the top left example here is just a local simulation, so we're just simulating a patch. And in that case, you need to just define some boundary conditions. So it is that if a particle goes like crosses the edges, then it can like be re-injected from the opposite edge. So it's also possible to do local simulations.
Sorry, you're fine. I was going to ask if there are any SPH applications where people also treat radiation transport.
Yes.
In a gray patch. And
yeah.
Better than that.
No, absolutely. So there are different possibilities actually. So the first thing you can do is just to prescribe, for example, a heating or a cooling term in the evolution that can adapt to the local conditions. For example, you want a cooling rate, a radiative cooling rate, which depends on the temperature and the density of the fluid, so you can just prescribe it. Otherwise, something that is very, very interesting, and I think you are working a lot on this, is to couple the hydrodynamics with a radiative transfer code, so that you have these two codes, the hydrodynamics, for example, with Phantom, with a radiative transfer code that are talking to each other. So at each time step, you give the information of the simulation to the radiative transfer code, which can compute whatever you want, can compute like a realistic velocity, temperature field, and then like heating, cooling rate, whatever, give it back to the simulation, to the hydro simulation, evolve the hydrodynamics of that, and do it again. This is, of course, especially for 3D simulations, this is very, very, very expensive. So I showed yesterday an example of one of these simulations for protoplanetary disks, in particular for gravitationally unstable disk where they coupled the hydrodynamics with the radiative transfer. And this colleague told me that to run a simulation, it took him a year. So like for 20 orbits, something like this. We are not like. But yeah, so it's possible. It's it's computationally tough, but it's possible. Yeah.
So can you? You're asking something?
No, I was just thinking about your question about the about boundary conditions, and so my background's in planetary science, so I do collisions of solid bodies.
Okay.
With a different SPH code, but of course, when you're building this planet, there's often a core and a mantle, and depending on resolution and depending on which code you are, you do see a bit of this extended gap between the core and the mantle, where you see that the particles don't like to be at such a stark boundary. That changes when they get mixed up a little bit too. But I was wondering, maybe this still happens here if you have an equation to state for like hydrogen, and then you have some carbon dioxide.
Yes, yeah.
And then you might see some.
Yeah.
Okay.
Exactly, yeah.
That was my question. Actually.
Okay.
Very
Okay.
different gas phases.
Yeah. And I mean, another possibility also, if you want to add another layer of complexity, is also to implement a chemical network on top of your simulation. So you are simulating different chemical species in a given system. You can prescribe some reaction rate. You can build your chemical network and input it into the simulation. So the hydrodynamics will evolve according to these also to chemical reactions.
Yeah, I'm very interested in this splitting technique that you're discussing, because in the planetary science SPH community, I haven't heard of anyone doing this.
The adaptive particle refinement. Okay.
Yeah, I haven't seen this happening, and it could open up the chance like for dehydration reactions. Where you have if you have a hydrated rock and you heat it up, then if it wanted to dehydrate, then wherever the hydrogen go, wherever the water go, we would need to go into a new particle, but we don't have a way to do that. So, but if splitting is something that could be implemented, then that.
It's currently implemented on Phantom. Yeah, and I mean, as I told you, since you are like modifying particles, splitting them, you're adding some noise. But I mean, if you control it, it's good.
Just get the next student to work on that.
Okay. Other questions, curiosities? I guess. Sorry.
About the refinement.
Yeah.
You said the refinement is happening just in a fixed region so far.
You can play with this actually.
So, for example, in a molecular cloud, I can set this splitting like in things like above a density threshold.
Yes, you can. Yeah, you can. You can, for example, decide the splitting region as a function of the density of the simulation. You can center a splitting region on a sink that is moving in the simulation. So this is what, I mean, I think that since Phantom is mostly used for accretion disks, this adaptive particle refinement was mostly used, for example, for planet disk interaction to try to resolve as much as possible like circumplanetary material. So if you put a sink particle that is a planet in a disk, and then you want to resolve as much as possible what's happening in the vicinity of the planet. So there your splitting region is following the sink. But you can also, for example, like also different layers of a disk, you can resolve them with different splitting levels. You can also like implement different splitting levels, like regions where it's a factor of 4 splitting, factor of 10, factor of 2, whatever you want. Yeah, of course, the more splitting you add, the more noise you also add, but it's controlled.
Is there any way to treat magnetic fields?
Yes, there is. I am not an expert. I always tend to avoid magnetic fields in my life in general, and in research life. But yeah, there is a way. So the Phantom is actually a MHD code. So you can also prescribe magnetic fields, evolve them. Honestly, I'm not super aware of how it works, but it is that as you have the equation of the hydrodynamics, you have the equation of the magnetohydrodynamics, you can discretize them in the same way I showed you before, and so you can basically also use that. I know that there are problems with the magnetic fields, especially with the conservation of magnetic flux. This is what I've heard at conferences. Yeah,
it's always a hard concern.
Exactly. Yeah, that's but I never used it. Yeah. Okay.
So what is the physical condition that determines the time steps when we integrate those equations? I assume that depends on density.
Yes. So the idea is that you have you don't have a global. You can choose whether to have like a global time step, so like a time step for all particles in the simulation, or individual time steps. Which is what we usually use. So each particle, like each group of particles have a given time step of evolution. So if I want to evolve the simulation, the global simulation from 0 to 1, maybe like for particles in the, I don't know, that don't have a huge dynamical range, I can just evolve from 0 to 1 in one step. But maybe there are particles that are moving faster, that are close to a center of gravity or whatever, or you just need like a finer time step. And so to go from 0 to 1, maybe it takes you like 2 steps, 10 steps, 40 steps, 100 steps. Yeah. So it's determined by the physical conditions, mostly by the, I think mostly by the velocity and the density of of the particles. Yeah. Lunchtime. Okay. Okay. I think it's a good time to have lunch and make a break. Sure. Okay. Okay, we can make a break and have lunch. Yeah. Thank you.
How long have you been done?
I am leaving this Friday.
This Friday?
Yeah. I mean, happy to reach out about because in my was like I was
It's just.
what would you use?
So local reference to Flash.
Yeah.
It was written by Alexander Huber. It's not really a very open world. We are becoming much more connected with Martin Wolsey, who does Bird, and then PKD graphic reading.
Yeah. I've heard. I think I've heard.
PKD graphic 3 now. This is getting highly parallelized. Right? They've done some billing updates.
Fantastic. Yeah. I don't know if you've heard of it.
And I modified only like.
Okay.
No, I don't know.
Yeah, this is developed in France, and they can have a trillion of patches. Of course, you need to have like in like a normal cluster cannot handle that code.
It's funny that
This is now probably 2020.
Follow the director of the.
We ran, Alex ran this database simulations.
Whatever, it's a professional
networking.
Only 1,000 at
stories.
I mean, not state of the art anymore, but it's good. It's pretty good for getting so we have this website of all sorts of all of the different conditions with the large range of Earth masses.
The director of the place is a very
Making things collide.
So
Yeah.
it's not me telling.
Yeah, so that's all we do, and my entire research has been looking at clumps of
Okay.
information to
Okay.
Find that they ask for.
So that's why I asked like clumps.
Yeah.
I'm interested in initial conditions as well, but this code is, homemade and, it's had your outdoor considerably of our developers over time. Where it seems like your group is.
Yeah. Yeah, I mean, it's
multiple developers involved.
yeah, no, it's really open source view and tend to be governments in like there are several professors every day.
Like this is, like this code was very, it's very, manufactured for.
Okay, yeah, so it's specialized.
So, one thing I've noticed is these the way that the movie form. There's often either this elongated tube or head-on collision and making space. So I was wondering if I could use as for. That's okay. So this is changes these things, especially for the. Yeah. But for this, urging this is how and then find out we can or have a
Yeah, you can. So really it's. You just need to clearly usually, I mean, it's very, very user friendly when you don't have.
As long as I'm not having.
Exactly. Whenever you have. So it's variable the potential but it is really important, which is depends on and yeah, and those there are a lot of it's like it's public. There are a lot of tests that people run before.
A little bit more.
Okay, so tomorrow maybe?
It may break maybe erase the parallelization part. So
Yeah, I'm gonna be planning to add in physics, but, and then do you have are you scheduled for a meeting tomorrow morning? Are you free? Are that we so those six options, they're not in the morning.
yeah,
Can you just put it on the schedule?
yeah,
Sure.
You know how to get, if you go to the TAP website,
I can.
if you go to the TAP website and click on like lectureships, you should be able to find his schedule.
I know. Yeah, I'll talk to my advisor. My advisor is Eric Aspon.
okay.
So do you guys meet in person and just Eric calls in, or?
When Eric was around more often, we would all meet in person, but he's either in Patagonia, Norway, or here. And
Yeah, no, I know he's not here.
Yeah.
most of the time. I'm wondering, the rest of you at least get to meet in person?
Sometimes.
Just all go on.
It's been a lot of Zooming lately. Yeah.
I didn't know he was in Norway too. I know he's in Patagonia.
No, he's
Not that nice Patagonia.
Patagonia, Arizona.
Say Patagonia and Arizona. I know. I realized as we were talking that you was.
So, yeah.
Actual Patagonia, no, there's Patagonia, Arizona, which is about an hour or so south of here. It's kind of like, it's very beautiful, like deserty, something like has a ranch or something.
Yeah, he has like 2 horses. Yeah. No, he was in Oslo for a sabbatical, like
Okay,
what should have been like 6 months, a year ago, but he found a way to extend that and continued finding ways to clear out.
That's the number of systems.
He's happy.
That's the biggest. Somehow now the numbers are very upfront compared to the text behind it. It feels more like a table than a figure.
I was thinking about it, but I never got to the stage.
I got too much. I am in the state of. Recently, she's very in the ledger. You could have these down there. And then isn't that kind of redundant information? Because then having like the personal systems that is below each of these timelines is information and much safer. These at glance, I would be unlikely to digest information.
Yes.
Express, yeah.
so I was looking at the Gizmo paper.
Yeah.
You know, Gizmo.
Yes.
And I'm trying to understand. No, a little more vivid information. And I was trying to explain to the student, which was trying to tell me that like, for instance, that's the NSPH. And I was talking about needing to add in duplication between particle penetration.
Yeah, that makes sense. Yeah, that makes sense. Like I was,
I
don't see they're doing that.
Myself. Particle penetration is a problem.
Yeah, no, the point is that the way that's described is
We have a time scale for when
a strong dependence.
get a car.
As soon as I want to, as soon as I can. Kind of.
So when it is you get a higher station, so a higher simplicity. When
Wow, so with the resolution, so you're saying it has nothing to do with. It's a resolution effect, not a physical.
Is this a damage or is this?
it's not very.
It's not.
There's no damage.
But the number
Like fourth edition.
defined how. Like, it's an
There's just a pain.
No, it's the number of you can make.
Light and reflection. You can just look at this.
How is that not a proxy for them?
I don't know. Oh, yeah. Yeah, because there's a reflection.
You may have.
But it looks like flash, like it's a.
Computed from 10.
There are problems with like mine.
HTF5.
Right. They run different simulation,
Like-
same astrophysical phenomenon.
HTF5 I use for the.
100 particles and 1,000,000 particles. I understand that shift density, the artificial is it will be higher.
We'll
low
use it.
particle concentration. But I'm considering.
Well, I think, I
This
think you.
Yeah.
Even this part, I heard it happen.
Right, I typically think of.
And that-
Artificial
This
density
looks
being
like-
the problem.
But maybe not enough for them to call it
Capacity.
Analysis.
market as well.
Oh, okay, I'll just.
And they have this. random things.
Because it's more like. What's the carbon people were selling it. I realized those were space. Because eight.
And, yeah, well, both agents.
Exactly, yeah.
Sort of flexible, I think, yeah, so.
Okay.
Yeah.
And
If you want to sit, I can come interrogate you, because I was just like, could not figure out
you
why.
wanna sit there?
I
You
can
can
sit.
have lunch.
Yeah. Yeah, so that's what I'm still trying to understand. I'm still trying to understand why this happens. So yeah, it's a function of H. It's a function of H and H. Okay, but then for a given. So yes, I'm still not understanding. I mean, other than intuitively that things are worse at low resolution and that low densities correspond to low resolution. Seems like, yeah, there's something I'm still missing.
Yeah, no, I see, okay, I don't think I have
Like,
a very clear physical explanation. Let me think about it.
because if I go to low. Yeah, and I guess I'm still trying, I'm trying to understand, there must be some scaling of like that fixed total particle. Like for. So you have some total number of particles. There's a minimum resolution, there's a minimum density that you can, there a minimum resolution that you continue to calculate things at, or is there a minimum density that you can resolve? Like, I'm not trying to think about, how should I think about this? So let's say I have let's say I have an SPH simulation where I have sent, I put 90% of my particles in a hydrostatic blob on the, at some coordinate origin, and I send off 10 particles. I explode 10 particles off towards it. There's some point at which I say I have only one particle, and therefore I can't compute the density. If I have one particle that's.
Yeah, no, so the idea is that you want to have like, okay, the width of the density. Particularly this is not internal. You have a number of particles that are usually contained.
Right, which is, based, and I understand the iterative solve for that. This is, I guess, I was wondering, do you just end up like not being able to converge? But yeah, so what happens? So you've got like one particle over here, and H gets big.
Yes, H gets too big because it can't find any.
Right.
Part.
And then does the code ever crash?
Yes, it does. So
Okay.
the code is not, the speech is not dealing with strong density rate. I have a hyper resolved even and a very low resolved.
Yeah, I think I got something. I see.
But you don't have.
What a struggle.
I'm pretty spice tolerant.
That's the wrong answer.
I have.
Or
Really happy with spice.
you get stuck in some new rabbit iteration loop because it
You
can't.
get stuck there. You get
Okay.
stuck in the density calculation, yes,
Okay.
because you can't find enough neighbors in order to work with the density.
And does it crash? Like, is it like,
Yeah, it stops.
will Phantom say if you don't converge on rho and H in some number of iterations, it just stops?
Yeah, basically the time steps, so you have the time steps in the formations and one of it is the density calculation, just explode, so it just gets stuck there.
Okay. But then is that related to why you get particularly high effective viscosity and low density regions? Is the artificial viscosity proportional to the smoothing length?
Yes, it's a smoothing length. Yeah, and.
That's
yeah,
why.
So, okay, like
Okay,
say.
now I
This
can-
smoothing length, the resolution standard.
Yeah.
So, no, yeah, exactly, yeah, it's related to the
So when you-
smoothing length.
Right, because
Yeah,
you have this iteration between smoothing length, this is why I was confused, because you have an iteration between smoothing length and density.
Yeah,
As you go to low density regions, total particle number H will have gone up. And so your artificial viscosity is proportional to the smoothing length, which has to get big to.
Yeah. sorry, it wasn't.
Related to that, in what situations should we use grid-based codes, and in what situations is SPH better?
In what situation, sorry?
In what situations should we use grid-based code, and in what situations SPH?
Yeah, I mean, apart from like the geometry requirement, which I mean, if you don't have if you have distorted geometry, it's usually easier to fix the SPH code. I think that if you have, for example, situations in which you have the very big density gradients, for example, I don't know, wind in protobinary where you lose a very small amount of mass, immensely, but a very small amount of mass compared to the total mass, then SPH won't. Indeed, for winds, usually people use grid code.
Yeah, so I'd say, yes, if you wanna, I guess, if you wanted to resolve a low density flow, SPH would be terrible. If you have if you're trying to do just like a turbulent box with like a supersonic turbulent box with shocks, I'd say be inadvisable to use SPH, you could do it,
Yeah,
would be.
and also very low viscosity systems. You need, I mean, you can do it with SPH, but you need pretty high resolution.
Not me, but some people I know would say always use a grid-based code. Which I don't necessarily agree with, but
There's definitely a contingent on both sides that would say, I'd say there's more people who do use grid codes who say,
Yeah.
you should always use a grid code.
Right.
Right, there are, right? If cost is not an obstacle, right, there are some ways in which you could argue that like, if you put throw enough grid cells at something, you probably converge. You converge faster, maybe. But if you wanted to study a blob that's advecting supersonically, you don't have a grid code that does advection, has an advection scheme, like. Like, but one of the big things in grid codes that made it possible to do some of the problems that you can do more easily in SPH were advection algorithms. So imagine a Keplerian disk simulation. The grid codes that do those well have an algorithm that basically advects the grid along with the Keplerian shear, which is the fastest velocity of the system. And so then the fluxes that you're calculating on will then update some background shear. And that's exactly what you get with a SPH code, because the material derivative contains that advection term. So you're not trying to solve, like you're, I guess, in like left hand, you're talking about the Lagrangian. So should I think of like a Lagrangian as being in the frame, Lagrangian is in the frame co-moving with the particle?
And then not owning it at all.
So even in a grid-based code, you're solving the same equations, right? But in the Eulerian picture. So how do you, I'm guessing you would face the same problem with discontinuities and shocks, even if you have a grid.
At some point made
Is something that you're like a bit about some.
Yeah.
How, because I mean, it's hard how viscosity.
If you compare.
I mean, sometimes it's also.
Sometimes it's explicit, sometimes so in grid code, sometimes people just.
And then you don't need to.
So you can solve the Navier-Stokes equation instead of the Euler equation, where the Navier-Stokes equation is the momentum equation with the viscosity in it. And then you just set the viscosity, and then that's a very clear way of doing it. And then otherwise, it basically is showing up as, yeah, an error term in your flux. Avery can step in and tell me what I'm saying that he doesn't like, but like, so that's it, the advantage, the one advantage to dealing with discontinuities in a grid code is one of the most common modern ways of solving for the fluxes across grid modes is using steam, which is basically solving. So you're saying, I'm gonna treat every boundary as a shock, because fundamentally at some scale it is a discontinuity. And so if I just apply basically the Rankine-Huguenot shock conditions at that cell, then I can capture that shock with some fidelity depending on some, I guess, choices in your solution. And so you're, rather than smoothing a shock, you're saying, I'm gonna treat everything as a shock.
Find that in the.
But the bad part is that if your grid is static, then when you have very high velocities, your error in your solution ends up being proportional to the velocities across the grid. So that's for high velocity flows could be bad. So is there anything else I should have said?
No, just every boundary is a shock.
Every boundary is a shock.
Pretty good
So
at shocks. Yeah.
actual shocks are okay.
Also, is it easier or more difficult to add additional physics like radiative cooling or star formation in a grid-based code versus SPH code?
SPH is pretty. I mean, it just simplifies some equation that
we're not that
everyone is so consistent. It's like it is the escalation. I think with codes in general, I also went there with this error line of the negotiation.
But it depends on what you're trying to put in.
It doesn't.
I would argue that
Also.
it's probably easier to implement ideal MHD in a grid code than in an SPH code. Right, because, right, enforcing div B equals 0 is a pain in SPH codes because you don't have any global, right? Because everything's like a locally averaged quantity. You don't have any control of the relative evolution of the magnetic field. Whereas in a grid code, you're just writing down, right, the ideal MHD equations, or series of conservation, conservation laws of PDEs, and div B is like always enforced by default.
Thank you.
So like all non-grid codes have like long sections devoted to like how they do divergence, which I do not claim to understand. Potential formalism.
I said before, I tend to avoid the MHD.
I don't know how, I don't really understand MHD solutions in this page, so they certainly exist.
Yeah, Japanese cars are.
But
Reliable and to hold it.
you wanted to simulate moving stars and add feedback,
But
that's gonna often be easier in an SPH code because it's like a piece of physics that's associated with particle.
Yeah.
Or like self-gravity is pretty hard in a grid-based code. Or the reason you need to do either a Fourier transform, which isn't really in the grid-based framework, or you have to do some sort of complicated.
Then I guess.
SPH is.
In SPH, it's just simply just kind of divide up your particle.
And you've already built the tree.
Yeah, you did. You already have a tree for the density calculation.
Where it's like, yeah, grid codes, getting self-gravity to work well is very expensive and.
And also the interaction with dust.
That's over.
It was over. It depends how you model it.
Yeah, I'm not convinced. I mean, there's the superparticle approach and then there's the fluid approach. I mean, to the extent you're doing the fluid approach, I don't think it's,
Yeah.
I mean, I think that is fairly.
I mean, I've never really explored those. Or.
do the configuration, or if you expect to have a better discount.
Right, this is why dark matter simulations are up in SPH.
But that's usually not the case unless it's something special, like.
You don't have, I mean, you want to, gravity matters a lot.
Yeah.
It's like it's the only thing that matters, right?
I think also that's why it's some formations like molecular collapse. I don't know if they're also, I mean, because I don't know.
I mean, we did a lot of Orion stuff back in the day.
Yeah,
Because it adapted
yeah,
that
right.
confinement code.
Yeah, of course, also your info.
Taking off the light of my.
That's not really smart for me.
Yeah, no, but
Because
next time you use the Orion.
That was Ryan, like Ryan, but, right, the problem there is that it's, again, it's. So the reason that the SPH simulations can be advantageous is because you're starting with a isotropic low density region and you wanna, it's, you don't end up having that much. You don't care about the low density regions at the end of the day, but you have to like track the flow to small scale,
Yeah.
right? And so you either have to have a mesh that's collapsing or like adapting to the flow or.
Yeah, and I think also one of the biggest advantages of SPH is that you have actually hard you can track it. And with the grid, we were discussing the other day, maybe a bit more sometimes. But yeah, you have hard to see if you want to track how particle move, you can just look at position at different times.
Right now to that survey.
Yeah, so tracers are very, that's a big limitation, I'd say, in fluid simulations. It's like you can construct streamlines.
On the housing.
You have a
new survey.
You don't know, like, the fluid that used to be here. You wanted to like watch how it, like, those, like, if you imagine like injecting, like, doing chemistry and you want to change the chemical composition of a blob of gas here. And then see how those things move. It's very difficult to do that in a theory code without putting in some extra tracer field. Whereas in SPH, it's like, well, it's just a very natural thing. You can just ask, well, where did that particle go? You can just trace it for all time. It has a number.
I was thinking about that, but then when you have splitting, it starts getting, or sinking.
Yeah. If you split, because there are routines to split particles with the resolution locally.
All of my visualization routines would break if
Yeah.
order of the list, because
Yeah,
I'd get around it. You would just have to query the
Yeah.
ID number, but
I've never splitted particles in my simulation.
yeah.
I mean, this was a big thing about 10 to 15 years ago. They were like really trying hard and then everybody just had to give up on doing particle splitting.
Yeah, but yeah, right, but now, you know, Rebecca Nilo.
Yeah.
She managed to.
She's going back to it, okay.
Yeah, no, she managed to make it, so now it's working very well, and I mean, of course, there is a little bit of noise created, but now it's done like conservable quantities. They still have some problems with the splitting particles, and also taking into account gravity, it's making it a bit more difficult, but it's understood, but
Oh, you would do, so splitting scheme would work better in simulations where self-gravity is more off.
As a bridge, if you go north.
So probably difficult for planetary applications then.
There's a.
Depends on what you're doing.
Depends, yeah.
I mean,
More.
Yeah.
Or more.
But yeah.
So are you doing like collisions with it? You're doing like asteroid collisions or something?
Yeah. I'm mostly working on the results of a big database of collisions that were run postdoc just before I arrived, but that was from series mass. So 10 to the -4 Earth mass to 10 Earth mass. Collisions, so a database of like 1,000 collisions, actually 1,250. Various velocities scaled to the escape velocity of that system. Mass ratios of 10% of the target to 1, and then angles.
And are you looking at cratering or like the?
These are similar scale collisions, so what we'd call it a giant collision, where if the impactor is really greater than 1% of the mass of the target, it's beyond cratering regime. So this is looking.
Just like moon forming.
This is everything in between. Half of our database hit and runs, where the impactor mostly survives, So this is going to be accretionary or disruptive collisions.
So what's the goal of that?
The goal of the database was to have is to map what is happening at all of these different things. So a machine learning model has been run on the output, so that way we can say arbitrary 30-degree collision at 2 times the escape velocity of a Mars-sized object. What is the accretion efficiency of that? That kind of thing.
So the goal is to basically be able to, like, if you had some persistent for a collisional history to predict the outcome for a given body or something.
Yeah, or for solar system and body formation scenarios to not have to pause the simulation every time a collision occurs between 2 protoplanets, but to have a quick check of how much mass should actually be transferred here, and we can actually predict what the outbound orbit is if it's not a perfect accretion, how much mass. And then I've been working on debris since then. 1 to 2% of that mass is converted into other particles that will survive. Yeah.
So like a subgrid and body simulation.
Yeah. Yeah. But yeah, it's been, SPH has so much inherent data side of it. Like, so even though the initial objective was just to get the net accretion efficiency of these, I mean, I've been digging through these simulations for the last 4 years already, and there's so much detail on the debris that is formed and how many clumps are going to be produced depending on the collision angle and nothing on that. It's a lot of information. We haven't even barely touched temperature variation, but how much heating is input to a body depending on the impact energy and the material. And
yeah, do you have like a multi-part equation of state in these simulations?
Yeah, these simulations are all with forsterite and iron differentiated bodies. So two materials. Yeah, it's an Anios equation of state for that. Starts getting outside of my. It's getting too deep, too much deep.
Let's see sunroof roller park. Wait. It's probably not something you want.
So with these astro SPH, like star formation, we were talking about like photo, like talking about light transport and that kind of energy. If you have enough mass, that's like star formation would be occurring, and like fusion reactions would be occurring, and energy would be produced. So how is that included? Is there?
So in pretty much any hydrodynamic simulation you're doing, that's all a subgrid model, and you're not resolved. I mean, so there are some, we get through Renzo's does some stellar astrophysics, right? There are simulations where we're resolving stars. But in a star formation simulation, stars are point masses.
Yeah.
And they have properties. So you could inject energy and momentum that could flow.
Okay.
This is a grid code or SPH. Based on what you think is going on, like you could say for a given mass and a given age, you could compute the nuclear reaction rate and the luminosity, but you're not resolving that.
No, not resolving the process, but you
can inject the energy back into the dome.
because it would matter, right? Like
Indeed, the temperature matters, heating.
Yeah, that's going. That'll be local heating greater than what SPH, like just the density of. Yeah.
The temperature from the background, the radiation field can be very much stronger.
Yeah.
I have heard of this.
It's up to you how when you want to get. I think we'll get started again at like 12:30. You want to finish that break?
Go get coffee.
Yeah.
Would you like an espresso?
Fine, thank you. Thank you.
Then for the black hole simulations, it could be replacing a black hole with a sink. Then I think you said like capturing the rotational.
Yes. Usually with black holes, you use potentials because depends how close to the black hole you want to resolve. Because if you want to resolve close enough, you want so like non-Newtonian effects. But yeah, you can evolve the spin of the black hole as well, according to the accretion. Yeah.
I imagine it'll be pretty convenient to have sync particles in your codes as a for post-processing, and that wherever a sync exists is probably a local clump. So then you can use that as for the plumb finding of neighbors around that particle, because this can be expensive.
Yeah.
And otherwise, if you're just checking the gravitation of everything to everything.
Yeah, no, indeed. I in a paper had to find clumps without using sinks. It was a long procedure.
Yes.
Yeah.
So in protoplanetary disk simulations, how important is cooling? Because when I do galactic disks, if you don't cool the gas, then it puffs up. And so how important it is for your disks?
Now it's important. So usually, like most of the protoplanetary disk simulations are locally isothermal. So you really don't evolve the internal energy there. So you just evolve the velocity and density, and you prescribe the temperature as usually a power law as a function of radius. So you don't evolve it. If you want to evolve it, you can use, for example, an adiabatic disk. So you can prescribe a given cooling law. And I know sometimes people do it when they have planets to study different, for example, morphologies of the spiral driven by the planet. But yeah, usually it's something like a degree of freedom that we don't use in protoplanetary disk simulations. But we will run now a simulation also with cooling for in order to trigger gravitational instability. In that case, may be useful because you want this to cool down. But yes, otherwise, for example, I don't know, like that simulation there of a planet disk interaction, it's locally isothermal, so temperature doesn't change, which is a limitation. It's also very helpful, but is of course a limitation. Yeah. And usually the temperatures are prescribed as a function of distance from sync or sinks particles. For example, if you have a binary, you can use like a modified power law, which takes into account the distance from both stars. Same if you have a flyby, so stellar encounter. So.
You could do magnetic fields with that. Have there been studies of like magnetorotational instability?
Yes. Yeah. Actually, yeah, you can recover magnetorotational instability with SPH. Yeah. In field work on this at some point.
Yeah.
But Phantom doesn't do magneto, does it?
Yeah, it does.
Oh.
It does. Yeah, it does. I don't know the state of that part, but it does. Yeah.
And the development has been purely open source. Is Cambridge is your local home where there's a lab working on this, or has it been?
No, so it's mostly developed by Daniel Price, so by the first author in Australia. So their group is one of the strongest group in SPH. So develop a lot of different routines, and then of course, other groups in all around the world like this expertise with Phantom. For example, the group I come from. My PhD in Milan, here was a big group in SPH, so like people working on this code, especially. So my PhD supervisor is one of the co-developer of the code, and there are other groups like also interested in different aspects. For example, in Belgium, there is a group interested in post-AGB stars with SPH in the around the world, and yeah, actually in Cambridge I'm the only one working on this now, but yeah. Here in the US there is a group in Las Vegas using it. Yeah, Rebecca Martin using it, and who else in the US? Phantom in particular.
And I guess Cassandra Hall.
That's right, yeah.
She's in the US.
Yeah, she's in Georgia, yeah.
She's not exactly like she's not a big group. Yeah.
No, yeah. There are a couple of groups in the UK, like in Leicester, there was a big group using it. And yeah, what's in the
not so much, yeah, penetration outside of Georgia.
Saw a paper from Jay Bay with it.
he uses actually the grid code.
Yeah, but
He'll do cross-code comparisons.
yeah,
Yeah,
we
we did,
work
yeah.
with Jay Hall.
Yeah.
He was working.
But he mostly.
But yeah, he mostly-
bar, I think. Yeah.
Yes.
Do you find a lot of agreement between similar simulations and other codes?
They do, yeah, like let's say within the limits of the different codes, you can find a pretty good agreement. So for example, we worked on this benchmark of different codes, both as one is so use Phantom as SPH code and then different grid codes, so using different numerical schemes. The benchmark was on the kinematics, so planet-disk interaction, and under a kinematic perspective, there is a very good agreement. And also in
Yeah, we had a paper in
Santa Barbara,
2022 at Santa
yeah,
Barbara.
Rico worked on the
Yeah, with the lead author is Duffel, Duffel. Can't remember if you've got 2 Fs and 2 Ls or 1 F. It's 2022, it's on circumbinary disks. And so there was a big code comparison with a wide range of different grid methods and SPH as well.
and I think it worked
There was a couple cases where there's some systematic offsets for the SPH codes relative to the grid codes, and also things in 3D relative to in 3D and not 2D, which is perhaps physical. So at the end of the day, there are some, like, it can be difficult to actually simulate the same problem.
Yeah.
Because of the way that you have to set up the two codes. And so sometimes it can be hard to differentiate whether or not the reason that your results are different is because effectively you really had two kind of different initial conditions.
so with the boundaries, I think it
Right.
May be completely.
Yeah, these comparisons can be historically quite hard to pull together. And stars, I have seen or heard that some people will avoid it just because of how difficult it is to get the comparison going, but also because you don't want to find out how much work there needs to be done too.
There is an art to writing a paper on this that involves not making people angry.
Yeah.
You accurately describe how things do or do not. And sometimes people are not willing to engage in that level of
I see.
care and writing. I'd say Paul did a very admirable job. We're grateful that he agreed to lead it.
Yeah. Okay, so now we can use Phantom. And so I think you already have the instructions to download the code and to basically make it work on your laptop. I don't know if did you receive the instructions before? Okay. Does it work? Have you tried?
I managed to compile it with a set of case. I did not try to run it.
Okay, no, that's fine. Other issues there?
I only cloned. I haven't even tried to compile.
Okay.
Hopefully it's not cloned.
Okay. It should hopefully. And yeah, so before really using the code, I want just to show you what are the different steps one needs to follow when using Phantom. So first of all, just download the code. So with git clone is fine. And then what you need to do is to choose a setup. So there are some standard setups you can choose, and these setups are basically describing different physical situations. And so there are a huge number of setups actually. So you can find inside this phantom build makefile.setups file a list of setup. I mean, reading the list, I don't think it's super useful, but in general, you can either simulate disks with just gas, with dust, with self-gravity. You can simulate galaxies. You can simulate stars. You can simulate like local instabilities, so Kelvin-Helmholtz instability and so on. So the idea is that each setup has a name, and what you need to do is just to choose the name you want. So the first step, and then we will do this together, don't worry, but it's just to, okay. Okay, so it's basically just to call in Phantom this file that is in the scripts folder. It's called the write-make.sh. Then you write the name of your setup, that in this case, for example, is disk, but can be whatever you want, and then make file. So this will create a make file in your folder, and the make file contains like the instructions, basically. And then to create the executables, make and then make setup. We're going to do this together afterwards. Now I just want to show you that it's very easy to run. I think if things work, it's very easy to run.
And something more on the software management.
Okay, so hopefully I can reply. Yes.
So the recommendation here is to clone the repo, and I didn't call any particular branch. That's what I got.
Now the master one is the automatic one, and it's fine.
And so, is that the recommendation for like people to start using it? Because I guess that people are developing the code.
Yes. So the idea is that you use your, when you want to run it, you use the master branch that you just clone from the repository. If you want to write something new, if you want to modify the code, what is advised is to create a branch. So you create your own branch, you write whatever you want, and then you merge it to the pull request, and if it works, it's then merge it to the master branch.
So there is no kind of quantum version number. I mean, I guess the commit hash could be the version number.
Yes, yeah. Yeah, usually
there is no explicit version.
No. I mean, sometimes I think Daniel sometimes create like a new version name, like version 4 point something, whenever a big part of the code is modified. For example, a couple of years ago, a new drug force routine was implemented. It was a very big part of the code, and so then he decided to make a new version so that, I mean, you were aware whether your code had that modification or not. Yeah.
Thanks. Sorry.
No.
Very question.
Okay, then when you so basically in this step, you create the executable to run the code and to create the initial condition, that is the make setup part. So then you want to create your setup. So you run this command phantom setup and the name of your simulation, and then the code will ask you some questions. I mean, it's very user-friendly, and it will ask a question like, do you want a sync particle? Do you want 2 sync particles? Do you want an external potential? Do you want, for example, if it's a disk, how many planets do you want in the disk? Do you want the disk to be warped? Do you want the disk to be flat? And so on. So it asks you a couple of questions, and then it creates a file that is called the simulation.setup. You open it, and then inside that, you can really write all the information you want. So it's like a file where it contains, for example, you can specify the mass of the system, you can specify the mass of the planets, mass of the sink, like orbital elements if you have like a multiple system, and so on. You modify it, and then you rerun the phantom setup, and this creates the first dump. So the dump is a binary file, which is basically the simulation. So it contains the information of all particles of the simulation. It contains position, velocity, internal energy, it is evolved, and so on. And so with this, you created the initial condition, which is basically a collection of particles that follow the instruction you asked for. So if you ask for, I don't know, for a star with a solar radius, the collection of particles will be such that the radius is a solar radius. And then according to the setup, you might want to relax stop or just start running. Then you can then after the initial condition is ready, you can run the simulation. So after this command, so the phantom setup is, as I told you, the first dump is created, but also another file that is called simulation.im is created. And this file contains like informations about, mostly about the running procedure. So end time, for example, the end time of the simulation in code units, the time within 2 dumps. So for example, I want to simulate, I don't know, 10 orbits of a disk, and I want to dump every 10th of orbit. So here there are all this information. And then there are 2 different kind of fruits of the simulations. So there are full dumps or non-full dumps. And so full dump is a snapshot that contains all the information. So information of position and velocity. So it's a heavier file compared to a non-full dump that is just an intermediate snapshot, which contains only information about the position of particles. So basically just density information. And this is useful, for example, if you want to create a movie after your simulation, you want to like have a lot of snapshots, but you don't want to like have gigabytes of material because you're just made for the analysis, for example, you're just interested in like what happens every orbit. So there you can choose how many full dump you want in the simulation. Then in this file, there are a lot of other information now. Afterwards, I will open one with you and look at it. But there are, for example, information about the equation of state, about like if you expect the simulation, I don't know, to lose a lot of particles, you can choose a kill radius. So all the particles that are outside of a given radius can be killed. If you have, for example, an injection routine, you can there specify how many particles per unit time you want to add. So a lot of different other things, and we will look into this later. And then when you're done, you just need to type /phantom simulation.in, and the simulation will start running. So this is how you run it on your lab. Of course, Phantom, you can run Phantom on HPC, so clusters. There, the idea is that you need to follow the same procedures. You need to change a couple of things in this in-file code because you want also to specify what is the maximum runtime that the cluster can handle. And then instead of running /phantom, you will just you need to create a submit file, which according to the cluster structure, you create the submit file and you submit the simulation. Okay, so what are the outputs of Phantom? So there are different kind of outputs. There are snapshots, so the dump files, which are called like name of the simulation _ and then the number of the output. So the 0 is the initial condition, and you have 1, 2, 3, 4, and so on. And then there are also different kind of particles. So there are different kind of files. There are, for example, the evolution files. So there are 2 kinds of evolution files. So like some global evolution and sync evolution. So let's start with the global one. That is this one. It has information about the total kinetic energy, thermal energy, potential energy, center of mass, a lot of information, maximum density, for example, the time step as a function of time for the simulation. And this file is unique, so it's not like the snapshot that is like 1, 2, 3, 4. This is just one for the simulation. And then you have also files to track the evolution of sync particles. So as I told you, sync particles can change in mass, in position, in spin, potentially. And so here you have the evolution file for the sync particles. So you have function of time, for example, the position, the mass, the velocity, the spin, the accreted mass, and other. So you have one file like this per sync. So if you have, for example, a simulation with 3 planets and a star, you will have four evolution file, one for the star and one per planet. In this case, if there are 3 planets, you will have 2. And yes, so these are the outputs. And to visualize the outputs, so in the instructions, there are also, it's also described how to download this and use this code called Splash. Splash is a visualizing tool for SPH simulations. It can be used for any kind of SPH simulation. So it works also with gadgets, SPH and other SPH codes. And basically, it allows you to visualize the output. It's really interactive. You can zoom in, zoom out, change the color bar, color scale, whatever you want. And you can create movies with this. And its strength is that basically to visualize the quantities, it interpolates these quantities on a grid. But this interpolation is not like a simple interpolation, it's an SPH interpolation. So also to visualize the output, you use the smoothing kernel. So it's consistent. And then if you want, for example, to analyze the dumps, I don't know, you want to study, for example, the I don't know how the total mass of the disk changes after a function of time, or you want to, from a simulation, I don't know, understand the power spectrum if you have a spiral, whatever, you can use this tool. This is a Python library written especially for specifically for phantom dumps. So it's called Saracen. You can just install it like this, and it allows you to open the binary file and read all the information you want, and also to visualize the outputs, always using interpolation technique, SPH interpolation techniques. And so in the Google Drive folder, there is also a Jupyter notebook with like a little script to how to use this Saracen, and we can have a look. Okay, so this is again the QR code for the Google folder. Okay, and so I thought about setting up 3 simulations and we can run them together and look at the output. So the first one is PDS-70. So PDS-70 is young stellar object. It's very famous because it has a detected planet, directly detected planet, and actually it has for sure 2 planets inside the cavity. And this is an observation. This is an ALMA observation of this system, and we are going to use the setup built by Claudia Toci et al. In 2021. Where she studied the migration of 2 planets inside this system, the accretion of planets, and also she found that there is a resonant locking between these 2 planets. So the position then is like, their position is in resonance, the one with the other. So to do so, we can start using the code, I think. So in the Google Drive folder, I think I can have it here. So you have the folder set up, you have a PDS-70 set up, just to show you, but we can build it together, but just for reference, you have it here. And okay, so let's open so I usually use it from terminal. So I have in this folder, I have Phantom, you see. So this is the Git clone version of Phantom. Okay. And what I do is I create a repository, let's call it PDS-70 simulation. Okay. So I enter here. Can you see big enough here? And so let's go back to the instructions. Okay, we want to do this. So we want to point to the Phantom folder and run this command script, write make.sh, and the name of the setup. In this case, the name of the setup is disk, because we are simulating a disk with 2 planets. So I know that for me, the Phantom folder is 1 folder behind. So it's Phantom, scripts, write make.sh. Name of the setup, which is disk, bigger than make file. Okay.
So the PDS-70 folder, are you creating inside the phantom directory or?
No, it's in another directory. Yeah, it's in another directory. Yeah, in another location. Yeah. Okay, so I created it, and you see now we have a file called makefile. We can open it just to show you what's inside. So there are some instructions. So here, where, for example, where is the directory of phantom? Splash directory is if you have splash, but now you don't care about this. The type of the setup is disk, and then like instructions that I honestly don't know what they do, but it's important to have that. Okay, so we have the make file. And now we need to create the executable. So if we go back, we need to type make. So basically, we are compiling the code here. To compile the code, we need a compiler. So the compiler we use is gfortran. It's the best one for Phantom. And so I have already like as a default gfortran as a compiler, but you can. So for me, if I just type make, it already knows that I want to use gfortran, but you can otherwise make system equal gfortran. Like this, okay? But I'm just gonna type make. And now it's compiling, so it may take a while.
Getting G4tran. We have to get G4tran.
So where in the make file do you specify the path to the phantom directory?
So when you create the make file like this, you need to like point to the phantom directory, and this will automatically write inside the make file what is the directory to phantom.
Okay. And you are creating the make file inside the simulation directory, right?
Yes.
I did the American spelling of disk, so I had to go back and
Yes.
see it.
I think it might work as well. I'm not sure, but
I don't think so, yeah. Provided it didn't.
Okay, here is the British spelling. Maybe also is it also in Australia spelled like this? Yeah.
In Canada.
Okay. So.
Canada, they kind of they're a little bit agnostic.
That's why not a lot of people in the US use Phantom.
Yeah, they can figure out the spelling.
No, I know.
So what did you say about G4tran? Before I type make, do I need to?
So it should be make system equal G4 run. You type this. Okay. Well, if it works, you will have like other two files here. One is called Phantom, which is the executable, and Phantom version is just pointing to the version of Phantom. Okay, so error, fantastic. In the make or make setup?
Make setup.
Maybe the same thing. So if you you need to write make setup system equal gfortran again. Yeah. Because or you specify in your bash that the standard compiler is gfortran, otherwise you need every time to specify. So then the second step is make setup.
The only real external dependency here is just one.
Yeah. Yeah.
I have an error in the base. Make one.
Sorry?
I have an error in the make.
Have you tried with make system equal gfortran as well? Let me check.
I've tried.
I knew somebody would have a problem.
You set up maybe. You set up before you set up. Very good case.
Can I look at the main file?
What? They probably pushing it. Okay.
Okay, so can you type make again?
So we're inside this folder.
This is where you have, yeah, exactly. It seems that the link with the path to the phantom folder is wrong.
What I did is just create a shell variable called phantom folder, hardcode the path in there. And that everything worked out. I don't know.
It seems that you see it says that that there is no. No, okay, no, because you created the PDS itself is inside the phantom.
Yeah.
Okay, no, it's probably better to be somewhere else then, and just point to that. Yeah. Otherwise, you can do that. So if you go okay, so maybe here, and then you just call the phantom the previous direction.
When I try to run make, it starts. When I try to run make, it starts like 200 or hundreds of is it possibly there's a double?
No, this shouldn't be. Can I have a look at the make file?
Yeah.
Yeah, you can open the. Have you tried just make or make system?
Systems.
Actually. It's weird.
Is it?
That G4 chain?
I don't think it's a geoportrait.
I did just make.
I did run this make. I might have made an error in the within Phantom 4 because while you were showing the slides, I had run this.
It worked before?
No, inside of the Phantom folder, I had run the script to find the to generate the file. But I may have overwritten the make file inside it.
You can try to delete the phantom the repository and just reflow. Yeah.
Who sync particles, then what would it do? Like I don't know, I'm trying to create the.
Okay, yeah, no, one.
Maybe if I'm ahead, maybe you talk about answer.
Yeah, no. Let's wait a second if somebody can.
Yes. I could just press 2 and then it answers my question.
Yeah. Okay. Let me know if
Yeah, I'll let you know. Just a second.
yeah.
Make it normal.
Yeah. Okay. And so you. Have you rerun the? No, you have to rerun. Now for me.
It's working.
Working. You just clone the.
Yeah, there's one.
Any problem when you were clone?
I can do clone.
Yeah, you better delete it and clone it. And see. We'll go a little bit ahead in the meantime. So let's go a little bit ahead. So the next step is to create the setup. Okay. So point/phantom setup. My simulation is called PDS-70, for example. And I just run this. So here it asks a couple of questions. So you want central objects. So this is valid for the star. Do you want to use a sinc particle or an external potential? Here we want to use a sinc particle. So 1. And how many sinks? Since the central object is a single star, here we want just 1 sinc. Then how do you want to set the gas disk mass? So usually we can use the default value that is 0. So we just choose the value of the disk mass. You can do it in other ways. Do you want to exponentially taper the outer gas disk profile? No, I mean, here it's not really needed. And it's just, this is just a way to prescribe the initial surface density. You want to read sigma profile from a grid file. So you can also specify sigma like in a file, but no, here we want to use the default one. Do you want to work with this? No. This to be eccentric? No. How many planets? So for PDS-70, we want 2 planets, right? Let me just check if I put the stuff. Yes. So then, so we want 2 planets. Just write 2. Enter time between dumps as a fraction of the outer planet period. So this is basically the time interval between 2 different snapshots as a function of the outer planet period. So here usually it's 0.1, meaning that with 10 dumps, I have an entire orbit of the outer planet, and this is fine. Number of orbits to simulate here. I mean, we won't run the simulation till the end, so we can just say 100. Okay, so here we are. Yes?
Question.
Yeah.
How does the code decide number of CPUs that it's using? Use OMP num threads or?
So on the laptop, I am not super sure about this, honestly. On the class, if you have a cluster, you need to specify it in the submit file for the cluster.
Yeah.
On the laptop, I'm not sure, honestly.
Right now, I'm running on my workstation upstairs, and it's 36 cores, and it's not using all of them, but it's not using all of them.
Honestly, I mean, I never use it on my laptop, so I am not.
I'm under the impression that it's using the OMP num threads, because through Logi Fortran, I loaded my Mesa setup that's set to 20, and it's using all 20 cores.
Maybe. I usually don't use it on my laptop, so I'm not super aware.
What was the command to start this?
What?
Okay, good.
Yeah. And now, so if we look back in the folder, we have different files, and this is a new one. So PDS-70.setup. So we can open it. Just have a look. So here it has several things. Okay, so first of all, the number of particles. You see, the standard one is 1 million. But here, since we are running on the laptop, we are using a lower number. Okay, so here I just have like the setup already compiled from a previous run, so we can just copy the thing. So I think for the laptop, it's worth using 50,000 particles, so we can like observe a bit of the evolution. So we can just write 50,000. Okay. Then distant units, accretion disk KU is fine, mass units, solar mass is fine. This is basically what we specified before, so we want one sync. Here, mass of the star. So the mass of the star is 0.8 solar masses. So we can just write 0.8. Okay. And the star accretion radius, this basically is the inner edge of the simulations, let's call it like this. So all the particles that have a radius smaller than this will be accreted. Just to check what they put, we can put 2 astronomical, 5, sorry. There was 5 there, 5 astronomical units here, okay, because we don't really care what's happening inside. Then this value can be modified. Of course, the smaller it is, the longer the simulation will be. J2 body, this is not very important here, so this is basically modeling the oblateness of the star. Then we have a lot of questions, a lot of things for the disk. Okay, so the first one are just the one we set up in the question. So how we want to set the gas surface density, if we want to read for a profile, tapering, blah, blah, okay. So inner radius. So usually the inner, so these are the quantities of the initial distribution of the particles. So we want the inner radius to be equal to the, let's say, to the accretion radius, which makes sense. So we put just 5. Then we have this quantity called the reference radius. So this is a quantity, basically, this is the radius at which we will define quantities like the thickness of the disk, the temperature of the disk, this stuff like this, okay? And here the reference radius, we can put 100. So all the quantities will be specified at 100 and then rescaled everywhere else in the disk according to the scaling laws. And the outer radius, we will put 100 as well. So the disk mass here, okay, the 5% is fine. We don't want to set stellar luminosity. So this is just how to set the Q index. This is the index of the power law of sound speed. So here 0 is fine, we don't really care. Then, so the standard surface density is a power law with radius. So here it has the power law index. You see sigma is sigma 0 times r to the minus p. So let me check. So this is 1. And the power law of the sound speed here in the setup from Tochi et al. Was 0.5. Position angle, this is basically how you want to rotate the disk, but it's not a physical thing, it's just how to visualize it. Inclination, same thing, since we just have a single star. Aspect ratio, 0.5. So the aspect ratio, what is the thickness of the disk, basically. And this is evaluated at the reference radius. So this quantity is called h over r, where h is the height of the disk, r is the radius. So here we say that at 100 AU, h over r is 0.5, meaning that at 100 AU, the height of the disk is 5 astronomical units. Okay? Desired, okay, this is the viscosity. Here we are. And desired alpha viscosity, because here in this setup, usually we have, so the disk is, the viscosity of the disk is characterized by this alpha prescription. And so here we basically specify this parameter, and the code will basically adapt the shock capturing viscosity in order to reproduce this value. And the value we want is exactly 0.005. Okay, so here we are. Temperature floor, minimum temperature floor is 0 Kelvin, but this is not a problem since we don't have, we have an isothermal disk, so we are not really modifying it. At the sphere around the disk, this is to simulate potentially a cloud, but we don't care.
That would populate particles.
Yes, exactly.
In a sphere.
Then planets. So we want 2 planets, and now we need to specify the orbital parameters of the planet. So the first planet, let me check. So it's a 2.5 Jupiter mass radius at 20 AU. So it's 2.5 at 20 AU. Inclination is 0. Accretion radius of the planet in Hill radii. So basically, this is like a way to quantify the accretion radius of the planet in terms of its Hill radius, and usually it's 0.25. Let me check it. Here is yes, it's 0.25. Then argument of periapsis and true anomalies just to decide the position. You can use the standard values, and we don't really care. As for the second planet, we want a 0.5 Jupiter mass planet at 45 astronomical unit. So we want 0.5 at 45, and the rest is a default. Thermal stratification, do we want this to be thermally stratified? Well, it's realistic to have a thermally stratified disk. Here we don't really care. So this is how the temperature changes the function of height, but it's fine like this. So, okay, we are done. So we save. And so now we are ready to create the first snapshot. So again, phantom setup, PDS.70, PDS70.setup. Okay, so this created the dump file. You see, if you look here, it gives you like a lot of information. So here it was setting up the particles. Here are quantities important, the particles, like this is related to the resolution. And then this is like, these are the gas parameters. So for example, you have surface density at a given radius, the Tumri parameter, for example, which is pretty low, I didn't expect it, but okay. And P, Q, M star, M disk, this two-star mass ratio, sound speed, temperature, and so on. And then properties of the first planet, of the second planet. It also gives you the resonances if you're interested. And okay, so if we look at the files we have now, we have this file, which is the initial condition, and this file that is the input file. So I already have Splash here, so I can visualize the outputs. And I want just to show you how the initial condition looks. So this is the initial condition. This is a snapshot of the integrated surface density in logarithmic units. This is one planet, this is the other one, here the central star, and this is the disk. You can look at the thickness, zoom in, zoom out, but this is just the initial condition, so it's really not telling us much. And okay, so now let's open the in file, and here you find a lot of like information. So, for example, the final time of the simulation and the time between dumps, this is in code units. So this is representing what we specified in the setup file. Full dump, like here I want a full dump every 10 dumps, so like every orbit of the outer planet. And here there are like numerical quantities, for example, the Courant factor, the DT, so these are related to the temporal integration. Here, shock capturing viscosity, some coefficients, you don't need to care about this. Here, equation of state. So in this case, we have equation of state 3 that is locally isothermal, but you can see you can have like a global isothermal, a adiabatic, a barotropic one, and so on. Then we specify also here, it asks the mean molecular weight of the particles. For a protoplanetary disk is usually 2.38. Here, like softening of the potential of the sink, these are all standard things. And here, this is probably interesting. So if you expect, this was the thing I was telling you before, if you expect to lose particles like very far away from where the action is happening, you can just turn them off. You can decide what is the killing radius of these particles. And in case you have black holes, you want to calculate gravitational waves, you can also do it, but yeah, don't care much. Okay. Fine. So now we think they're ready to run. So to run is just point/phantom EDS70.in. Okay. Now you see, these are all the time steps. You have different time steps according to different physical conditions. And here we have created the first dump files. Here is just how many CPU time, wall time, what is the efficiency of the code and so on. And also how much time is spent in a different part, like building the tree, computing the density, computing the forces, and so on. And yeah, so here we are basically creating a lot of files, and you can see that we have different dump files. So I will go to the folder where I already have run the simulation to show you a bit what comes up. Okay, so here, for example, I have 46 dump. I'm going to visualize them with Splash just to show you. So we're going to see, for example, how the surface density varies as a function of time. So we will use like column density in logarithmic. Okay. So we can go through the snapshots and you see, this is what is happening. So you see the two planets. The planets are not in a fixed position, so they can migrate according to the torque. And you see they are creating spiral waves. The spiral waves of one and the other planet are interacting, and you can go ahead and see what happens. See? It's very nice. I mean, the resolution here, you can see it's pretty low, but yeah, still, and this is what we can do on a laptop. And so just to show you what we can do with this, in the Google Drive folder, there is a Jupyter notebook where I am using this Saracen tool, this Python library to visualize this and to analyze these dump files. You can look at it at the Jupyter notebook to have a look. But also here, I think it's interesting to have a look at these different files. So you see, you have the evolution file for the free sinks and the global evolution file. So for example, if you want to look at how now let's do it with the Saracen, I think it's a bit better. So if we do it with the Saracen, so this is the Saracen code, Jupyter notebook you have in the repository. So you can install it with just pip install, and it should work and should automatically link with your Python. And so it's very easy to use. So you would define two variables, one for the particles and one for the scene particles. And the command is saracen.readPhantom, and you give the path of the dump. Then what you do, you need to calculate the density. The density is calculated in the way I showed you at the beginning. And if you look, for example, at the SDF, which contains the quantity of the snapshots, here you have, like for each particle, you see we have 50,000 particles as we set up. We have information about X, Y, Z, the X, Y, with Z, IH, which is the smoothing length. Alpha is just this viscosity coefficient on the location of particles. This is divergence of the velocity field, the time step of each particle, and the density. And we can, for example, do the same for the sinks. So X, Y, Z mass H is the accretion radius, basically. Softening radius, we don't have it. The accretion radius, spin, a lot of other quantities that are zero in this case because we are not considering them, and the velocity. You can render quantities as rho, like this. We can try also to render, I don't know, the smoothing length. I don't know if it makes sense or not. Let's see. Okay, so this is the smoothing length. And or
Why would the smoothing length in the denser streams be?
you're right, indeed, this is what I'm wondering. Is this a smoothing length? It should be. Weird. Possibly because it's a column integrated one, so it's not super intuitive. Yeah, but for example, you can look also at the velocity.
Yeah.
You see, and let's go back to the density, which is I think the only thing that makes sense here. Okay. And yeah, so you can also, for example, open this evolution file of the sync particles. For example, we want to see the migration of these planets, how they move. So we open this EV file. They can be opened just like with a load txt. And if I can show you one of them. These are the columns present, so time, position, mass, velocity, spin, and so on. So for example, I want to compute the radius of the planet, so the semi-major axis of the planet as a function of time. On the plane of the disk, so just cylindrical distance. So here I compute it, and you can plot them. So this is, for example, semi-major axis of the first planet, which starts at 20. You see, it has an eccentric orbit. This explains the oscillation, and it's migrating inwards. You can do the same also for the second planet, which starts at 45, and that's the same. Of course, the more you evolve the simulation, the better results you have, because you will find this resonant locking as in the paper. And of course, with high resolution, everything would be better. We can also try to plot, for example, the mass of the second planet. So let's check the mass is. Mass is column 5, so in Python 4. Okay, it's accreting mass, so it's increasing its mass. Okay.
We could pretty easily set up the same 3-body system in rebound or an n-body integrator and compare its evolution to.
Yeah, of course, here you have the hydrodynamics of the gas, which is not.
It would just be to show.
Yeah.
The effect of the.
Yeah, but you can. Yeah, definitely. Yeah, you can. You can do many other things here. You can also, for example, use the information of the simulation and post-process them with relative transfer code to simulate the emission in in dusk millimetric emission or scattered light, whatever you want, and see how this would look like with ALMA or with other telescopes. And okay, so any big questions on the on the running of the procedure of running the simulation? Some doubts, something you have not clear?
So it seems that it's automatically detecting the number of CPUs.
Okay, yeah, that part, honestly, I don't know. I would have said about
Based on playing now, I really think it's really like if you want to set it, you can set OMP_num_threads, which if it's unset, I think it's a standard Linux thing to then try to use all the CPUs that you have available.
Fair enough.
Say. But in my case, it was not seeing all, it was only using 20 out of 32, but because I had the variable set to 20.
Has anyone's simulation finished? Is it still running?
Yeah, you can block it. Don't worry. I mean, it's
Okay.
as you wish. Yeah. And yeah, I mean, this is very low resolution, so a lot of things are not, I mean, many things might not be completely correct, but if you perform it at high resolution, you get good results. And actually, I can show you the results on the paper.
Is that a gaming laptop? Are you running it on the high performance?
So this is the paper I was referring to. So this is the setup we run. And here what they did was to simulate the system. And then, so this is what should look like after a bunch of orbit. They also added dust to the simulation. We didn't. And so if you look at dust, this is what happens. So you have this very thin ring of dust. And what they did then was to compare the simulations with the observation. So this is the observation, and this is the simulation, like different run of the simulations with the post-process. You see, it's of course here is just high to high comparison, but it looks pretty good. Okay. Okay, so where are we? Oh. Okay, we can now go to the second setup I thought about. This is gravitationally unstable disks. This is what I usually run in my, like, every day of research.
So can we stop this?
Yeah, you can stop it with the Control-C, yeah.
1 million particles.
Okay, that's... Okay. Well, you find all the Jupyter notebook, all these things on the repository. So if you want to play with this later, you can. So now let's try to simulate a different system. It's always a disk, but here it's not an isothermal disk. So here we are also evolving the temperature because we are cooling the disk. So this is I'll show you a movie. So this is what we expect to observe, something like this. So this is basically a disk that is too massive and too cold that becomes unstable and develops this spiral pattern. So the instability is controlled by these parameters. So the idea is that CS is the temperature, is the sound speed. We are decreasing the temperature, so we are decreasing these stability parameters. Here, for the cooling, we won't use any realistic prescription. We will just suppose that the cooling time scale is proportional to the dynamical time scale with a factor of proportionality beta, meaning that at a given radius, we are cooling the disk with a cooling time that is beta times the orbital time scale there. Usually what has been found in literature is that for beta lower than 5, this number can be, there is a lot of, let's say, disagreement about the actual value, but like for small enough beta, meaning that for fast enough cooling, the disk will fragment. So the spiral won't be as the one I showed you, but will form like clumps. While for small, slow cooling, it will just develop a self-regulated state. So we will try to make the disk fragment in this case. And so, yeah, now let's go back to the terminal. We can create a new folder.
Actually, quick question.
Yeah.
Just because we're going to be pausing this simulation or control saying cancel. If I start the same command to run it again, will it?
It will start where you stopped it.
Okay.
You won't start from the beginning where you stopped it. Yeah. Yeah. So you can just stop it and run it later if you want. Yeah, this is also very, very good. So it will start at the last full dump. Okay. Gravitational stable disk, here we are. So we create a new folder, GI disk, I call it. But it exists, fantastic. They already created. Why not? Okay. Same thing as before, phantom scripts write make, but here the setup is different because in the setup we ran before, the disk was isothermal and non-self-gravitating. So the self-gravity was not completed there. Well, here we want self-gravity, of course. So The setup is called SG disk. Make file. Same as before, make setup with system equal G4 running case you still need it.
What was the name of the setup?
SG disk, which means self-gravitating disk, yeah.
Not recognized.
Are you using this?
This with the C, with the C, not with the K.
When you're doing this on HPCs or anything, do you ever need to make a container for this?
No, it's just git clone as you did for in your laptop is the same, yeah. Okay.
But can you show the last comment once again?
I run two commands together. You should make and then make setup. Yeah, if you put columns just.
And you have system equals G4 trans as a
In my bash, yeah, so I can show you. No, I have it somewhere. I don't remember where. It's so in the read the docs of Phantom. So in the official website, there are the instructions. Sorry?
The C profile.
CSH.
Maybe.
C profile. It is
RC.
Okay.
C.
Yes, here it is. Good. Okay, so here we have. Why don't make it work? Okay. Okay, we have Phantom and Phantom setup here, as before. And now we'll do the same as before. So Phantom setup, divide disk. Same question. So we want to sync yes, how many sync 1? Here, actually, since we want the disk to be almost gravitationally unstable at the beginning, so it's faster to run, we will set the total disk mass from the minimum to MEQ. So we just press 4. So we basically define what is this stability parameter at the outer disk, and then the mass will be computed accordingly. No planets. 0.1 orbital time at the outer radius, 100. Fine. Okay, now we open gidisk.setup. Let me just.
How many orbits do you?
Put 100, but you can. There. Okay, well, I think I remember by heart this setup. So, okay. Okay, so a number of particles. Let's use again 50,000, right? 50. Oh my. AU solar mass, star mass 1. So here, just for computational reasons, so these simulations, especially this one, are completely rescalable. So we are using AU solar masses, but can be rescaled to anything, okay? Here, for just a computational convenience, we use a very small radial domain, which can be then rescaled. So we use as accretion radius of the sync particle 0.25. And then here all standard. Inner radius 0.25. Radius of reference, which is equal to the outer radius, both of them 25, okay? So this is basically a disk from 1 to 100, 100 to 1,000. So it's just from 0.25 to 25, but can be rescaled, as I told you. Okay, minimum Q. So Q equal 1 is the threshold. We can use the minimum to be 1.1. And this will calculate the mass needed to reach this state. Luminosity 0, P index 1, Q index 2.5. We don't care. Indeed, since the temperature will evolve, the temperature profile will change in the simulation. So we don't care about this. No. And H over R, let me just check which one I picked. I picked 0.1. Okay. So at the outer radius here, we use a thicker disk, 0.1. So here, alpha SS. So usually this is actually an error in the current phantom repository. I raised an issue, but they still haven't modified. So they should not ask you this. They should not ask you the alpha viscosity for a GI disk, because the idea is that we don't really want to model the viscosity with an alpha prescription. We just want to use this standard shock capturing viscosity with the coefficient that we will change the in5. So here we put 0, but this value is actually not, it doesn't matter. So they are asking us a question that is not needed here. So let's just put 0, but it's, forget about this. Okay, here all the same. Save and quit, /function setup, jdisk dot setup. Okay, and so we created the initial condition and the in5. Okay, so let's open this and check if we have something to change. So this part is fine. I wanted to show you just the shock capturing part. So here, according to the shock capturing prescription that we are using, we have basically a minimum and a maximum shock viscosity parameters. You must think about them as like a sort of smoothing scale of discontinuities. So it's given in some units. So the idea is that the minimum is 0, so that we don't want any kind of viscosity if we don't have shocks here. So we don't want any like underlying viscosity in the disk. And the maximum is 1. So this value of 1, it's, I mean, there are a lot of papers discussing this, but this is like the standard value. If you want to resolve well shock, you need this to be 1. If it's higher than 1, you are over smoothing the shock. If it's lower than 1, you're not resolving it correctly. So this is from 0 to 1. We should be the standard one. Okay. Here, okay, here this part now is interesting because we have an equation of state that is adiabatic, because we want the temperature to evolve. And so what is changing the temperature? The PDV heating, so the heating due to the compression of the fluid, and also the shock heating, so the heating related to the shocks, okay? And do we want the cooling? We also want cooling. So we don't want just the disk to heat up, we want the cooling so that the gravitational instability can happen. So there are different, you see, cooling functions. You can choose from libraries. There is the ISM cooling, power law cooling, relative approximation. As I told you before, we use the very simple one, so just the cooling time scale proportional to the orbital one, that is beta cooling 3. So the option number 3. And so since we wanted this to fragment, we want a beta cooling pretty small, so we use a value of 3, okay? Floor temperature of 0 is fine, so we don't want negative temperatures, and the rest is good. Okay, so now we are ready to launch. Okay, this may take a little bit longer compared, maybe a bit longer compared to the one before. Indeed it is. You can let it run. I will just show you. Here I have 18 dumps that are enough to show the part. Okay. So I'm opening them with Splash as well. Okay, so here.
Can you give just a bit slower? I feel with Splash.
Okay, no, sorry. So here I'm opening with Splash all the all the files. Okay, yeah, I in the repository also attached the slash guide with all the instructions. So the idea is that here you want to plot, you want three quantities, one on the x-axis, one on the y-axis, and one like that is rendered. So for the y-axis, we want y, for the x-axis, we want x. And then what quantity do we want to render? We want to render the density. In this case, it's log density because I already said logarithmic, so 6.
I don't know what I messed up. I was trying to do this. That's what I wanted to see. Okay.
Then 0.
Okay.
Okay.
I don't know what I messed up. That's
okay. So this is the disk. And now I will show you what happens. So since we are cooling it and the disk is massive, you see it starts developing this spiral pattern. But the point here is that we are cooling the disk very efficiently. So you see it starts clumping more and more, and eventually just fragmenting, forming these clumps. At some point, the simulation will stop because here we didn't allow the creation of sync particles. So the idea is that these clumps will continue evolving in the simulation, and their time step will be so small because a lot of dynamics is happening around them that the code will just stop working. And yeah, so I can show you.
In my splash options, it's only showing density and not log density. So
no, you can so you can plot density and then show you. So basically, when you plot density, you have a give me a second. You have a plot like this. And this code is really interactive, so you can do a lot of stuff. For example, if with your arrow you go on top of the color bar and you press L, you can switch between a linear or logarithmic.
Oh, nice.
And if you want the logarithmic and you want to change snapshot, you just need to press S, which is basically saving the option, the visualizing options, and then you can, for example, you can also change the density. Okay, like you want like this, you can just press on this. You can change the color bar, the color map, sorry, whatever you want. You can, I don't know, zoom in on different clumps. So, yeah. Go back. You can play a lot with that.
Is there an option to turn off the kernel? The kernel
For the interpolation,
yeah.
you can change the interpolation.
So strictly the particles.
Yes. To 1, and you need to plot 0. The quantity 0 is just the position of the particles.
How do you move?
I'll show you again, sorry.
Snapshot?
Sorry?
How do you move to a different
with the space.
space?
Maybe you're opening just one snapshot. You need to open more of you need to open more than one.
Okay, got it.
So if you want to see just the particles, it's 2, 1, 0. Yeah. And you can go.
But you still have color for like the quantity?
Yes. 2, 1, 0. 6, no. You can. I don't remember how. It should be in the option, the render option. You can. I'm sure you can. You can also change the kernel if you want, like different kind of kernels. But yeah. So yeah, this is the particle visualization.
Nice.
So yeah.
That's interesting because in the when there was interpolated, you could see the clumps seemed so much more distinct, but then now you see there's only maybe 100 particles. Or
yeah, and for example, if you zoom enough, you wanna check the smoothing length. You press C around the particle, and this tells you what is the smoothing length. You see here is smaller, and here is bigger.
That's a good tool.
Yeah. See.
Yeah. Yeah, because every particle has it.
Mm-hmm. Okay. And okay, then I have the last simulation together. The last one may take long time, so we'll set up it together, but then it will take to me it took like an hour to run. Maybe for you it's a bit better, but I think it's very cool to see what happens.
When you're running, where in this running the simulation do you see like how close it is to finish? Or where's the percent completion?
So it's like according to the number of outputs you have. So for example, here we are simulating 100 orbits with 10 dumps per orbit. So you expect 1,000 dumps. So since we have 18 dumps, we are 18 over 1,000 done. Obviously.
Yeah.
Okay. So the last simulation is a tidal disruption event. So here we are using different stuff. So we are tidally disrupting a star, which will be our particles will form a star, and we will disrupt the star around a black hole that in this case will be just an external potential, won't be a single particle. I just want to show you a movie of another simulation, not of this one, just to show you what happens. So this is this is like a higher resolution, just to show you what happens. Okay, so you have then circularization of the material. Okay, so
is this in general relativity or?
Yes, yeah. So here the general relativity implementation here does not evolve the matrix as well. It's just a fixed matrix, but you have this general relativity precession and all these effects. Yeah. Okay, so the topic, let me just check. Fantastic. Okay, so where are we? Okay, new directory, TDE simulation. Let's go back, Phantom, strips, right make, and the name of the setup here is simply TDE, so tidal disruption event. Okay. Same thing as before, make, and then make setup.
Oh, I think it'll happen for this simulation as well, but for the last simulation, each of those clumps, this is getting to clump finding. How do you have tools already built in for identifying?
Yes, there are. Yeah, so there is a routine already implemented in Phantom to identify clumps and replace them with sinks.
Sure.
And otherwise, you need to do it like in post-process.
Yeah.
So you write your own clump finder. There are some of them already available.
Are they okay? So you use external clump finders, like you don't have one that's with Phantom or for post processing?
No, I do it in post-process. Yeah.
Okay.
Okay, this stuff is built, the same Phantom setup, EDE, and I think here it won't ask any questions. We just need to fill the setup file. Indeed. Okay. So you see tidal disruption in GR. Okay. So we have the td.setup. You open it. And here we need to decide. So mass units, the mass units will be in 10 to the minus 6, 10 to the 6 solar masses, so like the black hole mass. Mass of the black hole, we want it to be 10 to the 6 solar masses. So the accretion radius here, let me check what I chose. Okay, so I chose as accretion radius approximately the Schwarzschild radius of this black hole. If I remember correctly, so it's 10 to the 7 kilometers, and you can just write 1.7 times kilometers. Number of bodies to add. So how many stars do we want to destroy? Just one. Profile. So how do we want to set the density and the temperature profile of the star? We use two, that is polytrope. So we assume that the star is a polytrope. You can specify from file a density. You can also import the MESA models to in Phantom and evolve the hydrodynamics as well. So radius of the first of the star, 1 solar radii and 1 solar mass. So we are destroying solar mass type star. Number of particles always 50,000. Equation of state. Here we want an equation of state that is adiabatic because, of course, the temperature will evolve because you will have shocks. So you will have a lot of phenomena that will heat or cool the system. Gamma, we chose it 1.6. And mu, the mean molecular weight, is like a reasonable value, this one. Okay, so now there is this option, so relax bodies into equilibrium. So this is a relaxation routine before running the simulation. So the idea is that we will relax the particle distribution to have, like, say, a stellar structure that is respecting the stellar structure equations. We need to set a tolerance. 10 to the minus 7 is fine, but since here we want to make it a bit faster, we can just put 10 to the minus 6. Then you can decide also a maximum number of iterations for the relaxation, and you basically will create a dump each relaxation time step. This is standard.
I have a question here on the relaxation of the star. So clearly what you aim at having here is a density profile that verifies the star structure equation. If the star were to have a convective layer, I suppose for a TDE, you don't care because you're not going to simulate longer than a convective turnover timescale, so you don't care. But if you, like, say that you were to care, how would convection be treated?
You will probably, because I think that the relaxation works only when you choose a prescribed profile for the star, so either uniform polytrope.
Say that I give you a MESA.
If you give a MESA, I don't think you need to relax the star then, because you already, I mean, a MESA file is already solving the fluid equations. Am I right?
But the hydrostatic equilibrium.
You mean the hydrostatic equilibrium? Okay, no, you're right. So honestly, I don't know that because I've never actually done this. I mean, in principle, convection is resolved in SPH. So if you have a convective layer,
the convective velocity is going to be initialized. It's MESA or Kepler or whatever will only give you the mixing length theory velocity, so some effective output in space and time.
Good question. Honestly, I am not sure about it. Yeah.
Because I know, like, we played with grid-based codes and what my collaborators do, which I don't even know how standard that is usually they initialize a purely radiative star. Well, this with radiation on in the multi-D simulation too, and then they turn on the radiative flux, and that turns the radiative initial conditions into convection. But that all happens in the 3D simulation. So there is no mixing length theory at any point in these. And that's what I was wondering here, because you're passing something that has a density profile calculated using mixing length theory, and yeah, for a TDE, I'm not really worried, but say that I want my star to sit there in equilibrium and then do something to it, like throw a planet in it, or I don't know, pump some energy and make it lose mass. Then I would want probably to have the velocity field computed somehow self-consistently, and
I mean, yeah, I'm not super sure how it works for a star, honestly. Yeah, but I can try to have a look and let you know. Yeah,
I think, for example, Mike Lau has done like simulations on
Mike works a lot on
envelopes, and he must have had.
I'm sure there is a way to do it. I don't know what is, but no, there are a lot of people working on this stuff. So yeah, if you know Mike Lau, he's the perfect guy to ask. Yeah.
Yeah, thanks. Sorry for the distraction.
Okay, and then finally we need the parameters for the black hole and for the TD. So the first thing is the penetration factor. So the penetration factor is basically the ratio between the tidal radius of the black hole and periastron distance, and to have a tidal disruption event, we want it to be 1. So the star arrives at the tidal radius at its closest point in the orbit. We want the star's orbit to be, for example, eccentric. 0.8 of eccentricity is fine. And here there are other orbital elements. So, for example, the inclination of the orbit, let's stick with 0. And then how many orbits of the star we want to simulate here. 5 is okay. We won't arrive at the end because it will be a low resolution, and also we will destroy the star before. But okay, so here we are, point/phantom setup, setup. And now you see what it's doing is to relax the star. So like iteration of relaxation, and you see the that is like evolving the star. So the radius is changing, the ratio between kinetic and potential energy is changing, and also the density error, you see, it's increasing. Okay, so we did it. You see, we have 3 files for the relaxation. I can just show them to you. They are not interesting. I mean, nothing is really happening here, but so this is the star. You see, you start from like noisy initial condition, you get a smoother one. Okay. Done. So now we open td.in just to check if there's something to change. And I think here we don't really have to change many things. No, here we don't need to change it. I mean, if you want, for example, I don't know, calculate the gravitational wave strain, here it's true. Okay, so we can calculate it. And yeah, so now phantom, point/phantom td.in, and we can run it. So as I told you, it took a while to finish it, so I will just, you can let it run, and I will show you the results that are pretty nice. So here I have 360 dumps, as you can see. Okay, so here I had to adjust the view to have to see the entire TDE. So, okay, you see here you have the stars. I mean, I'll just zoom in for a second to show you. So this is the star. Okay. Well, let's go back here so we can see the disruption. So you see that the star is orbiting. Okay, okay, and you zoom in, you see that it starts being a bit sorted more and more. So the black hole is somewhere here. See? And whoa.
It's like visualization.
Okay. And here you also see the time. This is like 30 hours. I mean, here you see that we don't have much resolution, so we can't really. But yeah, this is the like you form a sort of a disk structure around the black hole. And yeah.
With these initial conditions, there's no unbound ejected.
No, here I started with a bound orb, so the initial orbit is eccentric. It's not parabolic or hyperbolic. You can also choose a parabolic orbit, and part of the material would be just lost. Here, I mean, I try to show you an ideal case, yeah. And you can also see what happens in 3D. Like we can, let's try to see what happens like in a John. So if we go a John like this.
If you wanted to do a problem for which setup doesn't already exist in Funnel, how do you go about developing a new setup?
So you need to to write, basically a setup is just a routine in the code that initialize the particle position and velocity in a given way, okay? So what I would suggest is to have a look at the different setup, see how they work, and basically just write your own setup.
But it's really just specifying initial conditions.
Yes.
For every part.
Yeah.
More than that.
No. Then of course you need to verify whether the physics you want to simulate is in the code or not.
Yeah, sure.
But if it is, then you have the initial condition, you specify the equation of state, you're done. You can model also you can also prescribe different equation of states, and here it was just standard ones, but if you have very complicated equation of states, you can just put them inside.
Has anyone tried to, for example, use the equation of state that NASA provides in this for consistency?
Yeah, it's possible to do it. I don't know if somebody tried before, but it's possible to do it.
Because can you give the tabulated equation of state?
Yeah, you
for
can.
Axis and then
I think it's already in the code. You can already do it, yeah. Okay, so I think now we need to, somebody's waiting, right? Probably. So I think I mean, this is everything I wanted to show. I hope you enjoyed this tutorial, and if you have questions, please ask. I'm around the whole week, but you can also reach out via email. And thank you guys.